Thank you, Brent, for the awesome XR presentation. We're all very excited about it, and this discussion will continue at the party later. So welcome now to the beginning of the Vulkan sessions. It's going to be almost all Vulkan, almost all the time for the rest of the afternoon. We have, I'm not going to go through these in detail, but we have a number of presentations on different aspects of what's happening, starting with the update, which I'm going to do with my buddies Piers and Yuriy. We have one 25-minute break in the middle. Use it wisely. The bathroom is a long way. And then more stuff, ecosystem developments and other things happening. Short break, and then the reception is not actually in this room. Brent was misinformed. It's actually in that room, but you won't have any trouble finding it. And thank you to our generous sponsors. There will be a certain amount of pizza and a certain amount of beer, which I look forward to very much. Without further ado, this is the Vulkan update, starting with the working group's view of what's going on. I'm Tom Olson. I chair the group, and I'm going to be assisted by two other members of the group, Piers and Yuriy, who also have other jobs, as you might know. I hasten to say this is not the Vulkan overview. It's the Vulkan update, because we only got half an hour. So I'm going to kind of assume that you know the basics of what Vulkan is and how the ecosystem is organized. And we're going to focus on the update. What has happened since SIGGRAPH a year ago that we think is interesting, or we hope you will think is interesting, and that gives you some sense of the direction that we're going in. So we'll start with what's happening in the platform space. Applications, particularly focusing on applications that are different from the traditional Vulkan targets. Talk about what the working group is doing in ecosystem and new technology. And we'll close with some updates from task subgroups. We haven't talked about these much before. Task subgroup is a subcommittee of the working group that works on some larger, more ambitious, longer-term project, usually one that requires special expertise that not everyone in the working group has or even cares about. So these are groups that go off, have separate meetings, develop specs, bring them back, and we bash them together. So we'll hear from a couple of those. So without further ado, platform news. Big splash earlier this year at GDC when Google announced their streaming platform, Stadia. That is supposed to go live before the end of the year, just in time for Christmas. If you think of it as data center somewhere with a gazillion little tiny but very powerful consoles in it, you won't be too far wrong. Exciting for us, of course, is that Vulkan 1.1 is the standard API for programming the graphics in Stadia, and that's really cool. There was a huge amount of interest from developers. This is all I saw of the keynote, because that's the point at which they said, sorry, no more room, and I was still a mile from the entrance. One thing I want to say is that the Stadia team, of course, Google's a member of the working group, and the Stadia team brought a number of extensions to us to work on before they went live. Many of them are Stadia specific, but one we liked enough that we picked up and made an EXT of, and it's in the registry today. Pipeline creation feedback, when you call VK create pipelines and you do this heavyweight operation of turning state plus shaders into something you can put in a command buffer, pipeline creation feedback allows you to get back from the implementation information about did those things hit in your pipeline cache or not. And managing your pipeline cache is critical to getting hitchless or hitch minimized performance in Vulkan apps, so that's really useful information. We're grateful to the Stadia team for bringing that to us. Also from Google, they announced this year that when Android Q ships, which is like next month approximately, all 64-bit devices that support Android Q will support Vulkan 1.1. And that will help to make a more uniform target space in Android, as, of course, it'll be initially high-end devices that do that. But it's a big step forward, and I'm excited about that. And finally, in platform news, presumably you all know how we approach the problem of Vulkan on platforms that don't allow you to install native drivers, for example, Mac OS. The Portability Initiative provides shim layers and tools that let you expose the Vulkan API, perhaps even link it into your application, and it translates all your Vulkan operations into Madill or DX12 or whatever it needs to be for the platform that it's running on. Molten VK is the macOS iOS version. It's by far the most mature, and there's a lot of stuff shipping on it today, including a couple of games from Valve now that are Vulkan only on macOS. That's Underlords and Artifact, but also lots of other things from other groups. The Google Filament PBR renderer is a research tool, which is really cool. That runs on macOS under Molten VK. Current focus of this group is to get Molten VK to pass the Vulkan conformance test. Tricky because it only supports a subset of Vulkan. And the Vulkan conformance test, if you didn't know, currently contains 460,000 separate test cases. So it's a lot of engineering work to factor that into stuff that can run and should run under Molten VK. But they're making good progress. So that's platform news as I see it. In the application space, of course, there are lots of games shipping on Vulkan. And that's awesome. It's why we did this. We're incredibly excited about it. But the really good news is it's kind of business as usual now. Not that it doesn't take heroic efforts sometimes. I'm looking at Yuriy there. There's a lot of work involved in sometimes, but it's what Vulkan was for. It's happening. We're thrilled about it. But because this is SIGGRAPH and our focus is what's different, I want to talk about what's different. So I want to talk about things people are doing in the application space that are not the traditional game port or game engine. So if you were here last year on this stage approximately, except it was in Vancouver, this logical stage, you heard Erik Berdahl from Adobe talk about a project that he did with Google and CodePlay to port a very large library of OpenGL compute shaders, recompile them to run, and be able to dispatch them and run them on Vulkan. And he did this in the service of an Adobe internal project, which they were calling Rush. And the idea was to take their industrial strength, GPU-accelerated video processing and effects engine and make it run everywhere so that they could provide a seamless video editing experience on any device you have in your hands. And so this was what he was trying to accomplish. Fast forward to this year, it's a product. You can go to the Play Store now, and if you have an appropriate device, there's a list on the Play Store page that you see there. You can download Adobe Premiere Rush, create and edit awesome videos, upload them to your favorite social media platform, and also share them with Adobe Premiere Pro if you're that class of user. It runs on all of the recent Samsung Galaxy S's, all of the recent Google Pixels, recent meaning 2-3 years, and some OnePlus and some other Samsung devices. And the list is growing, and they'll take feedback. So if you've got a device and you want it to run, tell them on the page. The scale of the project is daunting. Several 100,000 lines of OpenGL C code passed through the CL-SPIR-V compiler. Erik claims that he modified about 100 lines of the code base, and that's all. All of the rest was done by the compiler. Pretty awesome achievement. One thing that I like about this sort of at the meta level, it really validates the approach we took. Early on, we made this decision, Vulkan will not have its own dedicated high-level shading language. We'll define all the functionality in terms of SPIR-V, and we'll make SPIR-V be sort of, there's a Venn diagram here with lots of overlap and some corners. The SPIR-V that's understood by Vulkan and by OpenGL has a very high overlap, and that made this project possible. Very exciting. Other things happening. Nothing's really happened in this space yet, but we're getting increasing rumbles from the computer-aided design community that although they're very conservative and they've been happy with OpenGL for a very long time, they're thinking about Vulkan. And this makes sense because if you think about it, compared to games, CAD applications tend to make absolutely silly numbers of draw calls, and they tend to be very CPU bound. And Vulkan is good at that, right? Helps with your draw call overhead, helps with your CPU loading because you can multi-thread. So it makes sense that they should do this, but they're telling us, as they look at it, Lots of things, we can't do it now because you're missing too much stuff that we just have to have, right? We were never going to put in stippled lines to make Epic or Unity happy because they don't care, as far as I can tell. But the CAD guys need them. So as of 2 days ago, there is now an extension, EXT line rasterization, which gives you GL lines. Probably not going to ship everywhere, but all the desktop guys who have ambitions of supporting CAD applications will absolutely support it. And there's more stuff under consideration. One other thing, this is a little bit meta, but Vulkan was conceptualized from very early. I mean, in the first days of the Vulkan meetings, when we were skunkworks, we argued a lot about the level of abstraction it should provide. And the game developers, and particularly the engine guys, were adamant that they wanted it to be basically a hardware abstraction layer. They wanted something very thin and lightweight that would never hurt their performance, but that would just give them enough abstraction that they didn't have to adapt to every damn GPU on the planet. And then assume that people would build middleware on top of that. Now, I have to say, not everybody in the community thought this was a great idea. So my good buddy Dave Schreiner, who's a noted OpenGL hacker and educator, felt that we were going overboard with this and wasn't too happy with it. However, the game engine guys said they wanted a HAL, and so that's what they got. Sorry, couldn't resist. Kind of a dad joke. So, other things that are happening. Well, obviously, game engines target Vulkan, and they are a form of middleware, typically, although they often let you go right down to the metal if you want to. But other things that are happening, a lot of people are using Vulkan as a HAL and building on top of it implementations of the older, more traditional APIs. So you'll hear about Angle and Zink OpenGL versions that backend on Vulkan later in the second half of this session, so I won't talk about them. There's a number of people doing similar things for D3D, and I do want to talk about DXVK in particular for reasons which will become obvious. So DXVK, created by Philip Rebol, Deutschegin on GitHub, awesome programmer, begun kind of as his own, not exactly a hobby project, but a spare time project. And he got such good results that Valve said, hey, let us support you. And so Valve is now supporting him to make it happen. Out there in open source on GitHub, I raise it particularly because Philip was very proactive about coming to the working group and saying, look, here's what I'm trying to do. I'm having these problems. You know, there's functionality that I just can't see how to emulate, or there are fundamental incompatibilities in the way you've defined, for example, depth clipping, and the way DX defines depth clipping. Can you help me? And, you know, discussing with him and discussing the priority of it, we ended up actually with 5 extensions in the registry today that came directly out of issues that Philip raised. So happy about that. They're not necessarily things that you need to run out and use, but they're there if you do need them. If you are, for example, porting a DX application to Vulkan, you might find them useful. The other reason I wanted to talk about DXVK is that the impact has been pretty incredible. DXVK, executed in the context of Wine, is the heart of a project that Valve has called Proton, which is a package that you install on your Linux PC, and it allows you to run native PC games on top of DXVK Wine and with the other Proton sauce in there. And ProtonDB, where I stole these screenshots, is really cool. It's a crowdsourced database where you go, you install Proton, you install your favorite PC game, run it, see how it goes, report any issues, and rate it on ProtonDB. So this lower left here, you can see that to date, almost 6,000 games run to some degree under Proton. They're all ranked. If you go into this internally, there's a large number that are platinum, which means they run flawlessly. Basically, you take it out of the box, install it, it goes. Lots of others that don't. I mean, it's definitely a minority that are platinum. But lots of them are gold, which means you can play it, but you will notice some issues. So that's really exciting. It's enormously expanded what's possible with gaming on Linux. In the ecosystem space, there's lots of things happening in the tools arena, validation improvements, SDK stuff. Karen Ghavam and Mark Lobodzinski from LunarG are doing a lot of that work, and they're going to have their own dedicated session in the second half of the Vulkan sessions. So they're going to talk about that there. So I'm going to skip it for now. But lots of good things happening. Another thing I wanted to say is that I'm proud to say that Khronos now has a dedicated DevRel professional. Chris, would you stand up and wave? Hi, Chris. So, yes. Chris's mission is to help us professionalize our developer outreach and communicate better what we're trying to accomplish to you and help you communicate back to us what you need from us in order to make the things you want to do possible. So you'll see him at lots of game developer shows. He's out there beating the street and shaking hands and giving talks. He's, I should say, shared 50-50 between us and OpenXR, so he's a busy boy today with OpenXR coming out. New functionality, the other thing the working group works on. I'm just going to hit a few of the highlights. These are, again, since last year. We now have an extension which exposes float 16 and int8 data types as first-class data types in shaders. They're only supported in SPIR-V, right? We don't have any extension to support this in GLSL, do we? I don't think we do. But they are, I mean, this is one thing that in part is intended to support things like Adobe Premiere Rush. We can and probably will expose it in GLSL if it's, you know, I should have checked before I opened my mouth. I'm not sure. In any case, they are there. And so those types are understood by the engines, and it's all conformance tested, so that's good. It also gives you control in both 16-bit and 32-bit float of things like denorms, rounding modes, details of floating point behavior that you may not care about for graphics, but you definitely care for compute shaders. So that's cool. Descriptor indexing, that gives you bindless resources, which means you can change your model to where you kind of bind up everything you're going to need for a level or a large scene in advance in one huge descriptor set. And then when you go from draw call to draw call, you don't have to do all this rebinding. So it makes your, it improves your overhead of building your system. That's nice. Buffer device address is a quite new one. It was not around even at GDC, although actually Jeff Boltz gave a preview talk at GDC. So if you go to our State of the Union talk from GDC, you can hear Jeff give you the expert's view of what it is and how to use it. It's not quite pointers. It's basically kind of like having C++ references. So you can have opaque types. You can have a handle which refers to a place, to an object in memory. It is typed, but that object can be anywhere in memory that meets its alignment constraints. And you can store that in GPU memory. That means you can have linked data structures, which is incredibly powerful. So that's pretty exciting. And then last but not least, I think last year I promised you that we were working on new synchronization primitives. Now I can speak its name, Timeline Semaphore. This is actually not ratified yet, and it's not quite, or maybe it is ratified, but it's not shipping yet. But it's going to be shipping very soon, and it's so cool that James Jones from NVIDIA, who worked on it, is going to give you a talk and tell you what it can do right after the update here. So not public yet, but public real soon. There's other stuff, and I hesitated to show this slide, and I kind of apologize for it. But this is all of the KHR and EXT extensions we've shipped since SIGGRAPH last year. The first thing I want to say is you don't have to care. You don't have to know very much about this. I do want to say that all of these things were created in response to some need. We don't just make stuff up out of, in general, it's developers or hardware guys saying this feature is useful, please expose it. But they're there. What I would suggest is that you, every once in a while, flip through the extensions chapter at the back of the specification. Just read the overviews. See what, if anything, rings a bell that says, hey, I need that. We'll try to hit the highlights in these talks, as I've just done, but I didn't hit all of them because we don't have time. So that's the new functionality situation. We're now going to switch into TSG mode. Task subgroups are, as I said, subcommittees that work on big projects. Pretend for a moment that I'm Gabor Sinas. He's not here at SIGGRAPH. From AMD, there is a video TSG. Their job is to expose video encode and decode intimately integrated into a Vulkan engine. The hope is that as opposed to doing things with the shared memory extensions and doing everything at arm's length, this will give you more seamless, smoother, more elegant, maybe even more performant integration of video and graphics when it's ready. Target is to have it out at the first half of next year. First version, there will be a core extension that gives you video in general, and then extensions that give you H.264 and HEVC, and they'll build that list over time. So that's what's happening with the video TSG. Piers. Please welcome Piers Daniell of NVIDIA.
Hi. So I'm here on behalf of Pierre Baudier, who's the chairperson of the Vulkan Machine Learning TSG. Even though my t-shirt says I am AI, I'm actually Piers Daniell. So why machine learning in Vulkan? Is there a case of machine learning with interactive high frame rate applications? And definitely there is. Basically just doing image processing of the image before you display. For example, DLSS, deep learning super sampling, where you can render something at a low resolution and use AI to expand it and create quality that wasn't there. Or player bots. Basically, you're playing a game, you want to play against a good opponent. You need really good AI to be able to pull that off. And my favorite is character animation. So imagine a destructible world, and things are falling and things are changing, and you have characters in there moving around. You don't want to program every single movement of how it navigates obstacles and stuff. You really need machine learning to try and figure all that out for itself. So there's all these use cases for integrating machine learning directly with Vulkan. But how do you do it today? Well, you have to use interop. You use the usual Python TensorFlow or PyTorch or OpenGL, but then you have to interop with Vulkan if you want it with your graphics. And those interops aren't 100% efficient. Sometimes you have to do some copying if the memory's in different formats, or it's not very optimal. So the Vulkan ML TSG was created to start looking at these problems. You might think, well, I could just use compute shaders. Do I need anything more than that? Well, you kind of do. I mean, there are examples of people using compute shaders already, but none of them are using the hardware to its most optimal way. And in fact, it turns out it's incredibly difficult to write ML on any given hardware very efficiently. It's a very hard problem to solve. You don't know where to hide the latencies, how to use the registers, when to schedule transfers, and all those kind of things. It's incredibly hard. So the ML group was tasked to try and figure out ways of solving this. Now, I don't think there's one solution that fits all. So there's multiple things they're looking at. One of the things is to expose the low-level transistors on hardware that can accelerate this kind of stuff. For example, VK NV cooperative matrix is an example. Or just simply add improvements to compute shaders to make ML run more optimally. Or go slightly higher level and provide meta commands which encapsulate whole algorithms that can do a whole load of stuff, and each vendor can implement it most optimally for their situation. So if you're interested in finding out more, email Pierre at this email address. And right now, these are all the companies that are participating. Now, I just want to give a real quick shout out to NV cooperative matrix extension. So this extension exposed the tensor cores in Turing GPUs. And right now, it exposes FP16 types on the matrices, but soon we'll be supporting int 8 as well. With FP16, we can get about 100 teraflops on a Titan RTX, and about 80 teraflops on the lower GPUs. So if you want to experiment, this is one way to do it. All right, thanks.
Hello, my name is Yuriy. I work at Epic Games on the Unreal Engine rendering team. And I'm here to tell you a little bit about the ray tracing task subgroup. So about our task subgroup, we are part of the main Kronos Vulkan working group, and we are a collaboration between many hardware and software vendors. We work on the both immediate and future-looking specification design for ray tracing. And we work through regular meetings, both face-to-face and remote. Our goal is to deliver a standard Vulkan API extension for ray tracing on desktop platforms. This will provide the path for implementing ray tracing techniques in existing Vulkan renders. We aim to be consistent with the existing Vulkan principles, such as the Vulkan way of memory management and Vulkan way of resource bindings. And our work includes specification work and design work on both the core API extension and various supporting bits of infrastructure, such as SPIR-V extensions, validation layer, debugging and profiling provisions, and so on. We primarily target real-time rendering use cases, such as hybrid ray tracing and rasterization pipelines. But of course, we still keep in mind other possible applications, such as various interactive visualizations and interactive content workflows, as well as offline rendering and various baking pipelines. So the current status is, is that our current specification draft is based on the NVIDIA Vulkan ray tracing extension, and we are working towards some modifications and some additions on top of that. So a couple of examples are things like capture and replay support for tools like various debuggers and profilers, serialization of acceleration structures, CPU-side acceleration structure building, as well as things like indirect ray tracing and acceleration structure building. One very notable addition, or change rather, from the NVIDIA extension is the recursive or stack recursive ray tracing. Stack recursive ray tracing is made into an optional feature, which specifically means that implementations of the extension may choose to restrict launching new rays only from the ray generation stage rather than from arbitrary stage like it is possible in the current NVIDIA extension. And that does not preclude implementation of naturally recursive algorithms like path tracing or multi-bounce reflections. It simply means that such algorithms need to be implemented as a loop inside the ray generation shader. So if you're currently using the NVIDIA ray tracing extension and you would like to in the future port to the official Kronos extension, this is something to keep in mind, how your algorithm could be restructured into essentially almost a tail recursive, unrolled tail recursive form. We are aiming for substantial compatibility with DirectX ray tracing, DXR, while still maintaining to the core Vulkan principles, as I mentioned. We aim to release the extension as soon as there are 2 conformant implementations available. However, that's pretty much as much as I can say about the timeline. That's it for my update. Thank you very much.
Thanks, Yuriy. I did just want to slip in one more slide to say, if you're not good at subtext, I would like to point out that during my talk, there were lots of instances of, we got feedback from the community that we needed this, and we've now delivered it. So if there are things you need, we really would like to hear about it. We really do pay attention. We don't always give you what you want, but we try to give you what you need, and we're happy to talk to you about it. Give us input wherever is convenient. GitHub Kronos group, raise an issue. There's bunches of places you can do. The one exception for SDK issues, raise them at LunarG. I'm done. Thank you. Actually, sorry, I forgot we fused slide decks with our next speaker, James Jones of NVIDIA, who's a stalwart of the system integration group, going to talk about timeline semaphores.
So yeah, as Tom said, I'm James Jones. I work on Linux graphics drivers at NVIDIA. I participate in the Vulkan System Integration, TSG. And for the last, I'd say over a year now, we've been working on defining a new synchronization primitive for Vulkan. I'd like to discuss some of the features it exposes to applications today. So first, I'd like to go over the existing synchronization model in the hopes of highlighting some of the limitations that people have pointed out to us since Vulkan's been released. So Vulkan, by default, offers two coarse-grained synchronization primitives. There's VK Semaphore and VK Fence. VK Semaphore is for device-to-device synchronization. It has binary state, means signaled or unsignaled at any given time. It has auto-reset behavior, which implies there's a one-to-one relationship between signals and waits. So if you produce a signal, it can only be waited for one time, and that wait resets it to the unsignaled state. Because of this, queue operations can wait on and signal an arbitrary number of semaphores. So if you have, say, 5 waiters that want to wait for one signal operation, that signal needs to know in advance about those 5 waiters so it can signal 5 different semaphores that each of those different waits can consume. And that can be problematic if your application doesn't know ahead of time that it's going to have those 5 waiters. It might not know, think there's an arbitrary number. Vulkan semaphores are reusable, but only when they're in the unsignaled state. So in that previous case, if you wanted to reuse one of those semaphores after it took part in one of those 5 waits, you'd have to wait for both the signal operation and those previous waits to complete before you could ever signal any of those semaphores again, which means a lot of tracking in the application side of how those semaphores are being used. Further, another thing that causes problems for especially multi-threaded applications trying to build workloads across multiple threads is that you have to make sure that you submit all the signal operations prior to their associated wait operations. So suppose you have 2 CPU threads that are trying to build work for 2 different independent Vulkan device queues, and they're independent except for the fact that Q2 is dependent on some work from Q1. Well, suppose thread 2 is building the work for Q2, and thread 1 is building the work for Q1. If thread 2 completes its work and builds it and it's all done and ready to go before thread 1 is complete, it still has to wait for thread 1 to finish building its work and submit that work before it can submit the work that it's already completed. So that's dead time in the application or extra synchronization overhead on the application side, just because the synchronization model in Vulkan doesn't support that asynchronous nature. So that's VK Semaphore. VK Fence is an alternative for device-to-host synchronization, so signaling from the device and waiting from a CPU, for example. It also has binary state. Unlike semaphores, it has manual reset behavior, so it can be waited for multiple times. One signal can be waited for multiple times. And because of that, queue operations are limited to signaling one fence at the end of each submission. Fences are also reusable and also only in the unsignaled state. So again, if you had a bunch of submitted fence operations, you submit a signal to a fence and you submit a bunch of waits on a fence, but you have to wait before all of those signal and wait operations complete before you can again signal that fence object. So I think the best part about the synchronization model is that we did get it to work everywhere, and that was one of our main requirements when we first got Vulkan together. It had to work everywhere. Vulkan's portable. However, we have gotten a lot of feedback about this synchronization, all these synchronization mechanisms, and the parts of it that I've heard haven't been generally positive, so we put a lot of work into trying to eliminate all the limitations that I kind of outlined as a side effect of describing how they work here. And what we came up with is a new synchronization model based on what we call the timeline semaphore primitive. So right here in this slide, we have an example of a relatively complex workload. You have 2 device queues represented by green arrows here. Device Q1, you'll see it has some work submitted to it. Slightly later than device Q2 has had some work submitted to it. There is one CPU thread represented by a blue arrow. And at the top, you'll see we only have one timeline semaphore synchronizing all the operations that are going on all these different queues. And that's down from what would have probably been around 10 synchronization primitives needed with the old synchronization model. And the reason I say about 10 is because it's not clear you could have done all the things represented on this slide using the old primitives at all. You would have had to have, for example, extra waiter threads in your application, deferring operations, or faking some of this stuff. So you might have needed other primitives to get this all to work anyway. So I'm going to walk through a couple examples of some of the features now that make this slide possible. So first of all, timeline semaphores combine device to device, device to host, host to device, and host to host synchronization operations into one primitive. So you don't need to use fences for host to device anymore. You don't need to separate that from your semaphores doing device to device synchronization operations. And you can also support things that you couldn't before, like host to device synchronization, where you have some work submitted to the GPU and it's unblocked by a host signal operation. And host to host, where you're just synchronizing across multiple host threads, which arguably you could do with OS primitives, but when you have everything generalized, it just falls out naturally that we can now do that using Vulkan primitives as well. So you get efficient signaling in every direction, and I tried to highlight some examples of that here. In the green ovals you'll see here, we have device-to-device synchronization. In the blue oval, there's an example of host-to-host synchronization where a CPU thread is signaling and waiting for a primitive. And then, let's see if I can do this right live. In the ovals that go from green on top to blue on the bottom, we have host-to-device synchronization where a host thread is signaling and unblocking a device thread. And in the ovals that have blue on the top and green on the bottom, we have device-to-host synchronization where a device queue is unblocking work on a CPU thread. Timeline semaphore also allows one-to-n signal and wait relationships. So for any given signal operation, you can wait for it on as many different waiters as you want, including 0, which I think is really useful. There's no need to reset things and wait for them pointlessly if you don't care about them. You can just ignore them if you don't want to use them. So I've highlighted an example of that here. Right here we have device Q1 submitting a wait for the value 100, device Q2 submitting a wait for the value 80, and host thread 1 signals to the value 150, which since it's greater than or equal to both 80 and 100, it unblocks both those threads. So that's another point here to bring up, is that timeline semaphores always operate on a greater than or equal to basis. So anytime the value is above what you request, it's going to succeed. This is another big feature. Timeline semaphores support wait before signal. So what this means is you can submit, or you can begin a host wait or submit a device wait before queuing its corresponding signal or executing the signal on the host thread. So this eliminates the need for those extra synchronization operations I was talking about earlier on the application side. As soon as your work is ready, you can submit it, and you can know that as long as you know that later on, something else is going to unblock that work. I have 2 examples of that highlighted here on the slide. The first pair of operations is, you can see device Q submitting a wait for the value 40, and it submits that wait before device Q1 has even begun executing. And later on, device Q1 eventually comes along and unblocks that by signaling to the value 40. Going the other way from host unblocking a device operation, you can see device Q2 is submitting a wait for the value 80, and it becomes unblocked when later on the CPU thread signals to the value 150, as we showed before. And that should be obvious from all of these slides. Timeline semaphore allows having multiple signal and asynchronous wait operations in flight on one semaphore object at any given time. So the only requirement that you have to maintain from the application side is that the value of the semaphore always needs to be monotonically increasing. So you can never cause the semaphore value to go backwards. That would break the logic. Other than that, you're free to submit your work in any order you want to. You can have multiple waits in flight, multiple signals in flight, and they'll all execute as you would expect naturally, based on the greater than or equal to comparison operation as part of the wait. So those are the features that are enabled by timeline semaphores, but I wanted to talk a little bit also about how we integrated it into the existing Vulkan APIs. So timeline semaphores are actually just a special case of a VK semaphore object. So it's the same object handle, same object. It's integrated into all of the core VKQ operations that already support VK semaphore objects. So if you're calling qsubmit, you can just pass a timeline semaphore instead of a binary state semaphore. Additionally, you'll have to pass in the values that you want to signal or wait for those semaphores in an extension structure. Similarly, if you want to import or export timeline semaphores, that's also possible using the existing semaphore APIs. So you can just use the APIs you already have to share these across processes and use them as you would expect between different processes. And if you have other APIs that you're interoperating with that also support similar semantics, you can now interop with those more directly using timeline semaphores in Vulkan. Timeline semaphores are a functional superset of both binary state semaphores and the Vulkan fences. So if you want to, you could use timeline semaphores only whenever they're supported, and no longer use any more VK fences or VK semaphores in your application. And I would encourage developers to do that. It's a much easier programming model to build your synchronization around. And there's some caveats you get when you try to make the use of timelines with binary state synchronization objects that I'll get to later. The binary semaphore state of a VK semaphore is just replaced with a 64-bit monotonically increasing counter, as I mentioned. So it's the same object, but it has a different internal state. And the great part about having a 64-bit state in there is that you can use it to represent something other than simply signaled or unsignaled. For example, you could stash in there a monotonic timestamp, a frame count, or anything else that you wanted to keep in there that made sense to your application. We also added new APIs so you can signal and wait on semaphores from host threads, since that wasn't possible in semaphores before. And one thing that we really focused on here is that we understood from developers that they only wanted to write their synchronization model once. It's something that's central to your application. You really don't want to have two paths where you synchronize one way in one path and the other way in another path, because that's basically writing two versions of your rendering loop. So we made sure we had broad OS support. So initially, there should be support for Windows 7 through 10, Linux, and Android. And hopefully other platforms that support Vulkan will be able to add support as well. We did do some outreach trying to make sure, for example, the portability people will be able to support this as well. So we have high hopes that it'll work there too. So unfortunately, we did run into a couple limitations and compromises where we had to put some holes in the API, but hopefully we can get them resolved. So the biggest one I can think of is the Windows System Integration support. Right now, there's no support for timeline semaphores in VK-QPresent or VK-AcquireNextImage. So most applications that want to put something on screen eventually have to call these functions, and they'll have to use binary semaphores there. And the reason for that is that the OS and Windows System infrastructure is just not ready to support these yet everywhere. So some operating systems have support, others don't. And beyond that, there's also several API semantics issues we have to work through there. And we are working through those in the group, hopefully. But if you have input on how you'd like us to integrate these with the presentation model, please let us know. And this limitation is also kind of nastier than it seems at first glance. One of the problems is that while timeline semaphores support wait before signal operations, so you can submit in any order, binary semaphores still do not. And that still do not part applies backwards to any timeline semaphore waits that the binary semaphores are dependent on. So for example, if you have a queue and you've submitted some timeline semaphore waits on it, and then later on you want to use that queue to present your image onto the screen using a binary semaphore, you have to make sure that all of the semaphore signal operations that apply to that binary semaphore, as well as any operations blocking it, including the timeline semaphore waits, have their signals submitted as well. And that goes on recursively down the dependency chain of all the synchronization. So at least once a frame, applications still need to resolve all their timeline semaphore waits by submitting the corresponding signals. Also, we did put a lot of work into making sure that the API was the same everywhere for the reasons I mentioned before, but unfortunately we could not require import and export as a required feature everywhere. So the reason is that this relies on kernel level support if you want to support wait before signal everywhere. So right now, import and export will work on at least Windows 10 and Linux and Android devices with newer kernels or updated kernel drivers, but not necessarily on older devices than that. Also, while we made sure that you have a 64-bit state everywhere on all devices and operating systems, we had to limit the range of outstanding operations to 31 bits on some systems. So if you wanted to wait for the value 2, for example, and then signal to the value 3 billion, that might not work if you have one of these devices that doesn't support a large range. And the reason we had to put this limitation in is that some devices are going to implement this using only 32-bit hardware underneath, and this lets them hide the wrapping within the Vulkan driver, so the applications don't need to worry about that part. So you can still use the full 64-bit value everywhere, and if you're doing the most obvious thing and only incrementing your timeline value by 1 every time you do a signal operation, that should still work fine. Where you might run into problems is if you're trying to do something more clever, such as stash a nanosecond timestamp value into your timeline semaphore, then you might run into problems, because in that case you'd be wrapping every roughly 2 seconds, and that would potentially happen in real life. So most applications won't need to worry about this, but if you're trying to do something special, then you do have to keep this limitation in mind. And we're very aware that these limitations are probably going to impact some real applications. So, I mean, we're working to get them out of the way, and we tried to design the API such that they'll naturally go away in the future as support is added. So for the Windows system integration stuff, we're working on solving that within the working group. Hopefully we can resolve that as soon as possible. There are some external dependencies, but we'll try to resolve those as soon as possible. For import and export, that should go away naturally as operating systems and drivers update. And for the 64-bit value part, that should go away as long as the underlying hardware is phased out and goes away. So we've been talking about timeline Semaphore for a while, and people probably want to know when it's finally actually going to come. So the aim is to ship the specification in August. It's going through ratification now. It's not quite ratified yet. We're trying to have Windows and Linux implementations ready at launch. Native Android implementations should be coming with device updates. And I think the most important part here is that we're trying to make available a layer which will implement the entire API, and you can ship this application with your layer, and therefore assume timeline Semaphore support everywhere. So the goal is that people won't have to worry about using binary binary semaphores and Vulkan fences after the API ships, except for the exceptions above. If you ship this layer with your application or make sure it's available on the system, you can just load the layer, it'll implement the extension in devices that don't have the extension, and it'll naturally pass through to the native implementation where it's available. So I want to do a quick shout out to Jason and Lionel from Intel, who have been leading the spec development and developing the CTS and developing the layered implementation. Without them, we wouldn't have got it across the finish line even this fast. So big thanks to those guys. And if you have any questions, let me know. I'll be around today. I'll be at the beer and food event or whatever, so come up to me and let me know. Or I'll talk to someone else at Kronos. Thanks.
So we actually have 3 minutes now, but I think it's probably good if Julian comes on up and gets ready to speak. Our next speaker is, I have a list. Jules Urbach, yes, from Otoy. And we're going to need to swap laptops because I don't have your deck. Awesome. Okay. So while Jules plugs in, if you want to shout out questions for James or for me or for Piers or for Yuriy, you have like 2 minutes. Yes. Questions from anybody? So that's a no-fooling laptop. It may not fit on the podium. Or
I can do the presentation.
whatever you like. It's pretty good.
It should be.
Just make sure the lift is caught.
What do you think? Like this?
Sure.
Okay.
But where's your
HDMI.
HDMI? Oh, this is it.
Oh, perfect.
Okay. I'm just glad it's on that side. All right.
All right, can everyone hear me? Great. It's great to be here. I'm Jules Urbach, CEO of Otoy. Otoy's mission is to make the Star Trek holodeck real at some point, but in the meantime, we've actually been shipping products for a very long time that are focused on rendering, on graphics, on capture. We're very well known for our work in CUDA with OctaneRender, which I'll talk about. And next year, we will be shipping a version of Octane that is written entirely in a different language than CUDA. It'll have all the same features, so everything I'm about to show you is really going to be shipping on top of Vulkan, and it's a lot of work. We've never actually seen, I don't think, a production render shipping on Vulkan at this level. So I'll talk about some of the challenges we're facing, but also just describe sort of what we're doing in the long term and how Obviously now, our big bet on Vulkan is going to have a huge impact, I think, on everything that we're doing. We're seeing a lot better speeds. So back to the holodeck sort of as a larger, picture. I mean, it isn't something that we see as being hundreds of years off. We started, a lot of our team used to work out of ICT in the USC Graphics Lab, and LightStage is something we took out of the lab and commercialized, but ultimately there's a lot of work being done around volumetric displays. This is a spinning mirror that was actually able to take LightStage scans that were volumetric and display them volumetrically. So the future of holographic displays are going to be ray traced. They're going to have about a gigapixel per square foot. Well, I'll talk about that a little bit. And everything that we're building to support those displays with partners is really, at least on the Windows and Linux side, is going to be using Vulkan. And also the Vulkan extensions for ray tracing are very important to us. So a proof point of how well we're doing is whether we can actually ship all of Octane and everything that's been done on CUDA for 10 years on these platforms. And again, sort of our business is divided into these three parts. But in the middle, OctaneRender, it's been around for 10 years. It was really the first production GPU render out there back in 2010, and we've increased the things that it can do almost every 2 years to the point now where, we're ready to take on holographic rendering. We've got, machine learning is a big part of this. Real-time integrations are a big part of it. For those that aren't familiar with Octane, you may have seen the work done with the render, the CUDA version. This is the opening of Westworld and The Crown from Netflix. Marvel movies are rendered in it. So, it's running entirely on the GPU. There's no CPU code. And ultimately, the Vulkan version of Octane is going to be running 100% on Vulkan. And the challenges that we're sort of facing, not so much with the programming language, is I'll sort of describe how we're doing this port. We're rewriting everything in GLSL. We're getting rid of pointers that are in CUDA. This is from Ant-Man and the Wasp, also rendered in Octane, the entire title sequence. Important note that from the real-time perspective, Octane is actually free and integrated in Unity. You don't need to download anything extra. You can just load a piece of sample content and Octane will sort of kick in. And our path for supporting, taking this thing and getting it to work on Vulkan is actually also going to help us support Madill as well. We built a cross-compiler SDK that handles a wrapping layer around the different ray tracing hardware APIs that are around, including obviously the NVIDIA ray tracing one, where our team is part of the Vulkan group that's working on the ray tracing extensions. In the meantime, we're using NVIDIA's ray tracing extensions. The front end is being ported from CUDA to GLSL, and we chose GLSL because obviously there's a lot of great pipelines for compiling that to Vulkan and to SPIR. But in the end, we're looking at also supporting x86 and CUDA even. So we actually are doing a CUDA backend and building all the various runtimes. But today, with the work that we've done so far, we can run most of Octane on Madill and Vulkan with this pipeline. On Intel integrated graphics, even the Madill version runs on iPhone. So this is doing 8 bounces of path tracing, which is pretty cool. Octane Bench on iPhones work. It's roughly the speed of a decent discrete graphics card. So we think mobile, and whether it's Vulkan on non-Apple devices or Madill on Apple devices, is really important, even for production rendering. This is something that we just introduced and had working for the show. This is our Vulkan Madill version of Octane. It's zero CUDA code at all. It's actually working pretty well, and it looks great. These are production scenes. And so far, this is also using 4, I think, AMD Radeon 7 GPUs. It's looking good. It doesn't have every single feature in there. We're probably going to get there closer towards the end of the year. But we've done enough work now to be able to speak cogently about how the work from porting from CUDA to Vulkan's going, and the, sort of the pitfalls that we're sort of concerned about. Drivers, even in the current version of Octane, which actually is half Vulkan and half CUDA, we use the CUDA Vulkan interop. There have been some issues that are pretty serious, like we actually have to double the memory. We're hoping that those driver issues get fixed. And of course, we need to see standardization around ray tracing APIs. For us, it's actually very important. This is the high-res version, looks great. It's very important for us to be able to ship compiled shader code. We've got extensions for that. It would be kind of nice to have that like we do in CUDA, and also being able to link those binaries together are very important. So we've had discussions with each of the vendors, NVIDIA, Intel. We were a part of their event last night, and Raja and I were on stage talking about how we're going to bring this all to Intel graphics cards, and truly we need those extensions to Vulkan to make that work. So everything you're about to see from this point onwards is really talking about not just the CUDA version, but Vulkan now. So there's a lot of stuff that we've been building for a decade in Octane. We built our own SIGGRAPH system that doesn't rely on ray tracing hardware. It's pretty fast. We've been also doing a lot of machine learning work, our own work to essentially get really production ready denoising. The other tricky thing, which wasn't working until very recently in Octane, was we do have out-of-core geometry and textures working perfectly, and we have a ton of procedural things inside of Octane that are basically shader toy-like things that are written in open shader language. And here's an example of how Octane inside of Unity works. It's pretty fast. You can run it in game mode, full path tracing, 60 hertz. It's pretty nice on a single GPU. This is how the AI denoiser works. It is able to actually render just with a few samples. It can do really nice, almost final quality renders within a second. It is different than some of the stuff you're seeing in the real-time engines. Those are almost a separate path. And we're using cuDNN for this. So we're also looking at building a compute version that would run on top of Vulkan, and that work is in progress now. And of course, there are things that are totally outside the domain, again, of ray tracing triangles and other intersections, which is volumetric rendering. Shading and lighting is a really important part of the pipeline, so getting compute cores to operate fast. No matter what else you have with ray tracing hardware and even things like tensor cores for AI, you're going to need compute cores to do this right. This is an example of totally procedurally generated objects. These fractal environments are just built in OSL shaders. To that end, when we were doing the CUDA version of Octane, we built an OSL to PTX compiler, which is the intermediate language for CUDA. For Vulkan, we were doing OSL to GLSL, and then we're going to cross-compile that like the rest of the code base to Vulkan. And we've got a pretty rich ecosystem that we're supporting. There's like 26 different GCC integrations. We just put out Blender for free, Unity is free, Unreal is free. The rest are $20 a month to get all of them. So it's a pretty low bar to get into the ecosystem for production rendering. And especially with Unity, we have a lot of challenges. I mean, being CUDA only, obviously there really wasn't much of a choice until Vulkan was more mature, but we have millions of Unity developers that are, that need to have support outside of NVIDIA cards, even if those NVIDIA cards ultimately end up being the best performance. So we can also use that to import scenes into Unity. We view Unity and Unreal and Blender as really important test cases for us to be able to push this ecosystem out. We've had, just in SIGGRAPH, since we started to put out these versions, we're seeing thousands of users download these things, and we want this to work everywhere. So Vulkan for us is really a way to help make that support work cogently. This is scene conversion in Unreal. We've also been adding to these engines the ability for you to load production assets like OpenVDB files, and all of this, again, is going to have to work not just in Vulkan, but at the same speed as it's always worked in CUDA. As this year, we've introduced a ton of features, such as better volumetric denoising, layered materials. Unreal Engine also is introducing layered materials, so we want to sort of support that and match that. In particular, implementing this on CUDA was kind of tricky because we're actually, we have these different BRDFs that we need to link together, and we're just at the point now where we're going to start testing this on the Vulkan version, and we'll see how the speed works. But hopefully, it won't be too big of an impact. I'm just sort of going through some of the, more recent features in Octane. We've also, worked on procedural displacements that you can define entirely in open shader language, which could use things like tessellation. I mean, interestingly, when we're doing CUDA only, there's never been the possibility of mixing the graphic stack. In other words, doing hybrid rendering where you can rasterize and tessellate with the tessellation shaders and then also do shading. We might explore that, and ultimately we have that option now with Vulkan, and being able to mix graphics and compute. OSL is particularly a challenge. There's almost nothing in Octane today, that can't be, that can't be reprogrammed with OSL shading. Yes, you can do this in GLSL if that sort of language, but it also, OSL is an industry standard spec, and it's actually being adopted widely almost in every render. Arnold GPU just came out last night with open shader language support. It's going into Redshift. It's obviously in Octane. Pixar uses it. So it's really, if you're going to create shaders in a way that are portable and production ready, OSL is very important. There's a lot of ray tracing effects also that we need to support, such as rounded edges that are sort of outside the bound again of normal, just traditional shading and triangle intersection. We also need to have a pipeline where you can build your own camera lenses. And this is important not just for these kinds of effects, but also for targeting lenticular displays, holographic displays. As you guys will see, that becomes kind of important. Post-processing, again, all done in open shader language. And then we do have other machine learning things that we're porting to Vulkan as well, including super sampling. This basically is rendered in 1/4 of the time when you see on and off due to AI upsampling. And in 2019.2, which we just shipped at SIGGRAPH, we're adding even more effects that are more demanding on compute, random walk, which is sort of in films how you get really nice skin quality, going hair shading as well. And this is interesting too. Now we have procedural, totally procedural volumes that you can just generate from the ground up. You don't have to actually build them in Houdini or in TFD if you guys are Cinema 4D users. That's a pretty popular thing. Or Fume Effects, you can just create OSL shaders. We compile those into GLSL. Those will run on the Vulkan pipeline. And we're also looking at other really important interchange formats like USD and Hydra and MDL. And by the way, GLTF's a big part of our pipeline as well. I'll get into that in a minute. On the Hydra side of things, we've built a delegate, a render delegate for Hydra, Hydra, if you guys aren't familiar, is the interface for loading USD as a front end, but also then having any render play back. So Houdini at SIGGRAPH this week introduced Solaris, which is basically uses a Hydra system. Maya has it, Katana has it. It'll start to be in a lot more DCC tools, and we think it's a great way of sort of validating renders. And there is another case for having a sort of backend that works with Vulkan is very important. We want to be able to have this thing be portable and work everywhere. And we're also just working on other effects that are pushing sort of the envelope of being able to represent all sorts of scenes, including complex things like fluorescence and polarization. And so it's going to be interesting, and also non-photorealistic effects. And this, by the way, this kernel that we wrote here is written entirely in and for our new backend. So we actually have chunks of Octane fully working to this day and fully done that we know are performant. We're also building tools on top of the Vulkan backend system that are outside of Octane, like the sculpting system, for example, is a good indicator of that. We have the ability for you to do procedural computational sculpting. All of those shapes are basically defined in shaders that we are going to be running and computing in real time. And this is another example where having Vulkan and Metal, even in just a piece of Octane, is making a big difference. We can run most of the shading on a CUDA device on the network, and then the last part of the pipeline is running in on the local machine with Metal or Vulkan, and it works really nicely. And that's sort of an intermediate step that we've introduced this year, until we have a full version of Vulkan or Metal that can run everything locally. I do want to spend a little bit of time on RTX and ray tracing hardware because it's such a fundamental game changer for everything that we're doing. The only way that we've actually accessed this at all has been through two approaches. One is we actually had access to the Power VR, Imagination Technologies' early ray tracing hardware. It was very impressive. It was running on 2 watts and able to do hundreds of millions of rays a second. That's pretty nice. And now we have RTX, which is shipping in millions and millions of GPUs, which is amazing. And we're seeing from a 1080 to a 2080, 10 times the speed up in Octane. And in this case, that speed up is running with half of Octane in Vulkan. Like we've never, some people have done optics or DXR. We were one of the very first early adopters to use the NVIDIA ray tracing extensions to get to basically hook up Vulkan, mix that with the CUDA code, and actually ship a version of Octane this week, which really allows you to leverage Vulkan ray tracing hardware APIs at a very low level, and we were getting significant performance boosts. The optics backend for Octane was not getting 7.5 times the speed. It was closer to 30% faster. So for whatever reason, having low-level access to Vulkan really allowed us to tap into the hardware better. And I think for a lot of developers, having that kind of low-level access is important. So I think Optics 7 is now sort of out there, and it's got lower-level access. But for us, Vulkan has worked out pretty well. We're only mostly concerned about the drivers and the stability, and even having to currently sort of mix and match that with CUDA. But that's really the starting point for us. I mean, obviously being able to have ray tracing hardware through Vulkan and CUDA today is great, but we're developing an entirely new rendering pipeline purely in Vulkan, 100%. There's no CUDA at all that was ever used for this, and this is to give us noise-free viewport rendering. So we have Brigade. I don't know if you guys are familiar with it. We've been showing it for years. Some of that was merged into Octane just at the SIGGRAPH level, but we had a lot of really advanced and very fast noise-free shaders that needed a lot of compute power, but frankly, they're ray tracing bound. So these things run on a single 2080 Ti. We're getting basically noise-free renders. So if you compare the CUDA code on the left, running basically Octane as it is today, and on the right, the Vulkan version, by the way, on the same GPU with the same scene, that is actually showing the speed up that we're getting, both in terms of the noise sampling, but also just Vulkan, pure Vulkan is really fast. I mean, it's faster than mixing Vulkan and CUDA. We're not sure exactly how much, and of course it's not completely a fair comparison because the sampling is a little bit different, but the idea is that we ship this totally new rendering pipeline as part of Octane and allow you to ship games with it as well, and it's pretty cool. So that was sort of an early test, but here's another example showing fairly noise-free rendering. This is a single 2080 And we think that there's a whole market that can be, that can sort of extend our work with DCC tools into, real time. And you see that convergence happening pretty nicely with Blender, with Eevee, and Unity and Unreal becoming almost production renders in their own right for certain types of content. This is showing, by the way, different noise filters that we use, all written in, on top of Vulkan. And then, we've been looking at how to, that's a good example. Can we take production scenes and run them through the system? The answer is yes. Again, also just a single, I think this is a 2080 Ti, and this is running with the full lighting and shading, also on a single GPU. You can see it's getting about 60 hertz. So ray tracing hardware makes these things really, really easy. We have a Vulkan fallback that doesn't use the ray tracing hardware, but it is 3 times slower, so you need 3 times the compute power. But it's good enough for the Metal version, for example, to run an AR kit, which is pretty cool. And that's, obviously AR for us is an interesting, endpoint for the things we're authoring. And this is obviously showing the Metal version, but ultimately on a Vulkan, Android phone, it would work the same way. We also need to capture and ray trace the environment. This is obviously running live on top of the scene. And this, to me, is a great reason of why we sell our software and authoring tools to Unity and Unreal users, because they can build experiences with this, ship the render that we now have running on Metal and Vulkan on their, inside of their Unity or Unreal files, and get this kind of quality, and even blend that with their production pipelines from C40 or Max that are fed in there. And ultimately, we think that authoring on phones is going to be very important. So we see a lot of viral videos of people taking, like, here's the Unity, the Atom asset being put through Cinema 4D and rendered. And then if you have the ability to author this on the phone directly, you can build the same thing, and you don't need to have a desktop machine. So again, the iOS version is on Metal, the Vulkan version would be on other phones, and that, I think, is a super compelling use case for the future. The other thing that we've announced, I guess it's almost been 2 years, which is our blockchain-based rendering network. We do not have enough GPUs on the public cloud to do all the GPU rendering work for offline renders, so we built a distributed network. It is live. It is CUDA only today, because it's Octane only. We're bringing on other renders, but we're also planning on having Vulkan versions of Octane leverage many more devices. Those could be Intel integrated graphics. They could be Metal on for Macs, and ultimately we should be able to support Vulkan on any device that has correct Vulkan drivers, and that'll expand the network. Right now we've got about 14,000 GPUs. It's a lot of compute power, which is fantastic. So I want to sort of close out by talking about why this performance matters, and also what's sort of beyond the work that we're doing today in terms of AR and even VR and real-time and production rendering. This is holographic rendering. So this is basically, if you're going to do a 32K by 32K render that is, each pixel or subpixel is being rendered on a holographic device, this is what the data kind of looks like. Now, obviously, I'm just rendering it on a 2D, video here, but it is essentially each of those 6 squares connect together like the walls of a holodeck, and you have all the lighting stored, and you can trace into that, and it's very inexpensive. It takes a lot of pre-computation time, but once it's done, you have absolutely no real speed hit to doing that live. And the thing is, we need to do it live, so we want to actually get real-time ray tracing between hardware support and maybe cloud rendering to kind of solve these problems, because while this might work for a Vive or even phone-based AR, like we're running the light field renderer on the server side, and then we're streaming that to the phone. That works pretty nicely. You can even do that for AR without any tracking markers. Ultimately, what we want is something that doesn't require any sort of shortcuts, and that is, if you guys are familiar with the Looking Glass display, that's like a lenticular, I think it's got 45 views, but a true light field panel, something you would actually use to power the Star Trek holodeck, would have 100 subpixels at 400 DPI. In other words, it'd be 4,000 DPI, and you would basically have this thing like an LED video wall handled by the square foot. So we partnered with a company called Lightfield Lab, and I've seen the device. Others have, like Raja, the graphics guy at Intel, and it's insanely compelling. It basically is like looking at a true emissive holographic surface. It is just, you're just dealing with with 100 times the pixel density of rendering on a mobile screen, which is already pretty dense. And this is also going to be something that is many, many square feet. So the other interesting part is that these touchable light field display panels, they're going to have touch through ultrasonics, and the way that they're going to be shipped is as 2-foot by 2-foot panels. So they will be stitchable together. If you want to build a true life-size holodeck or a concert hall, and I think this is going to be targeting large displays, first, you again sort of stitch them together like the Samsung CS micro LED video walls. My guess is that beyond sort of, the large venues and theme parks that'll get these things first, where it'll really get interesting is when you can have a tabletop holographic surface like this where you can really run, and touch anything, and that will replace laptops and many other use cases. And of course, if you have many, many, many millions of dollars, you could take enough of these 2-foot panels, they could be stitched together and they can be curved and all these things, so you can build a real-life holodeck probably the next 5 years for that kind of investment. So to build this pipeline, again, all of our rendering work was put to use. We started by just doing, just to test how glasses free would work. We did head tracking, and we took the light field viewer, by the way, also written on top of Madill and Vulkan. And ultimately, this is what we were showing last year and this year at SIGGRAPH. We have a head tracking system with shutter glasses that gives you about the closest approximation you can get without seeing the physical display to what it actually looks like. And it's compelling. Again, it's hard to really show that in a video, but this last one here is one that I talk about a lot. I've seen this, the very first image we got on their display was this scene, and the surface of the display was where the wood floor is, and the coat hanger and the door were just floating above it, and you could take a magnifying glass to it or ground glass, like all of the rays are there. You can converge on it. It has depth of field in a way that is just magical. It's like nothing I've ever seen in auto stereo displays or VR and AR. And ultimately, the player for this is all running, on top of Vulkan with the ray tracing extensions to be able to compute all this. And we're going to need a lot of these. I think the 6x4-inch display needs about 2 RTX 6000s, which is a lot. So you imagine 6 times that for a square foot. You're at 12 high-end GPUs just to do a square foot of holographic displays. So we need more compute power, but ultimately the API of choice for this work has been Vulkan with ray tracing. And I'll sort of show how the stitching works. If you just have, again, the 6x4-inch panel at their offices, they have 2 of them. You can connect 2 of them together or 10 or more. The larger the surface area, the further out you can project from the surface. And it's a little bit like 3D TVs where if you were, you can see something really floating in front of you, but if you move too far to the left or the right, it goes out of your field of view, it gets clipped. It's no different with holographic displays, so the larger the surface, the further out these objects can appear. And if you build an entire room or cover your field of view with it, then you truly have a working holodeck. Lastly, open standards critically important. Inside of all the real-time stuff we're showing, we actually convert the entire Octane scene into GLTF, which we're also part of the working group. It's such a great format. It's super efficient. We really believe in open standards. The metaverse should not be, have any black boxes. So Vulkan's a big part of that. GLTF's a big part of that. Maybe at a higher end level, we want to bridge things like USD to that. I mean, they just serve different use cases. But we're, really big believers in the metaverse at large and open standards. So being part of Kronos is awesome. So I think with that, I'm good. Are there any questions? No questions. Oh, wait. Oh, sorry. Go ahead. I didn't see.
Do you have a way to stitch together the panels right now? And how hard is it to configure them, like to tune the colors and whatnot?
Yeah, so here's the thing. We are not making the panels. Lightfield Lab is, but since we work so closely with them, within the panels themselves, they're stitching together much smaller, high-density panels. And the thing is, the thing that goes over it, the little, diffuser, if you want to call it that, which is like this little nano diffuser, hides the schemes between those smaller things. So if you put together larger shipping panels, the same effect works as well. It totally hides the bezels and seams, both on a micro scale, a mesoscale, and a macroscopic scale. So it's part of that. And of course, for them as a production, making these production ready. I mean, you have the same sort of effects when you're trying to hide the bezels in a, LED video wall. It's going to work the same way. It'll hopefully be no more difficult than that. I mean, you might need a professional to set it up so it works correctly, but it'll ship in those configurations, and however you're configuring your TV or your video wall, it'll be no harder than doing so with micro LEDs that, like the Samsung wall, which are shipping, or near shipping today.
Thank you.
You're welcome.
Anyone else?
Oh, question in front?
How close do you think it is to being able to run on top of the molten VK instead of direct to metal?
We've tried both, and there are things that are missing in molten VK that are forced us to go and do things directly in metal. I mean, Apple actually featured the work we were doing on metal at DubDub, so we're very proud of how that works. I mean, molten VK is awesome. I mean, we actually have used it for a lot of stuff internally, but for everything that we need on the metal side, there are some pieces missing. But I think our developers might actually be in touch with the people working on MultiVK to help them out, because it's still a super useful tool, and I think it's great. I think that there's still pieces that we really need things in Metal to handle the way that we want, and it can't all just be done in MultiVK. So that's kind of where that's our real world experience. Maybe someday it'll change and we can all use MultiVK and it'll be fine. But we're really committed on making sure that Metal works absolutely the best way it can. I don't think there's actually much missing though in the MultiVK thing. I think we looked at it and they're pieces, but it's not like a huge delta from my understanding with my team.
Like integral imaging and stuff like that, it's fine. But for like true light field displays, we're going to have an API built from the ground up. Can you comment on that at all?
Sorry, I'm having trouble hearing.
So like integral imaging approaches, that's fine and all. But like for true light field displays that actually have diffraction and fringe patterns, and you want to have proper interference, like we're going to have to build an API from the ground up.
Drive the display. Is that roughly the question? Is what API would be used to drive that? One of the suggestions I'd have, and this is just work that we're doing in general, is remember that camera shader I was describing, that OSL camera shader? So the reason OSL is a little bit cleaner than GLSL and certainly other proprietary formats is that it is something you can translate to GLSL. And that OSL shader is how we drive the light field display. We're not doing anything proprietary. They just give us a pattern for where the rays are going, and then we feed that to the OSL camera system, which, again, OSL is open source. If you build a render that can consume that OSL camera shader, and it's really not that complicated, you could drive any of these things. You could drive the looking glass, you could do projections for VR. And I'm trying to sort of get people in the industry that are already adopting OSL to at least do that for production rendering so that you can actually render images that would, at least as a still or a movie, could run on the light field display. But if you take that and run it in real time, that's exactly how you could work with that. And it's not that hard. It didn't take us long to write that shader for their system, and it works.
So you mean from like for integral imaging where you have multiple layers, right? You're generating a pattern using a compute shader, right? But that's not like true holograms, right? So like, trying to generate an interference pattern,
No, it's not like that. It is an emissive light field display, and a hologram is obviously, if you go back to the real definition of it on silver and film grading and how the interference patterns are generated, that's a different beast. But ultimately the effect is when you shine a light on a holographic surface and you reflect the light field, the emitted light field is what we're going after, and how the display itself does that, or how any display would take, would emit rays for that is something that's kind of where we stop, and the API that we've been working with kind of ends. So,
do you have any thoughts like using compute or generating the attenuation pattern is fine, but like we need to build something from the ground up. Like we have to start early on. So like when you're doing a compute pattern, you do multiple layers, right? And you're trying to generate multiple views, like per degree. Like you're just generating 2 layers on top of each other, or multiple layers. Like multiple layers reduces complexity. We can talk offline about this.
Yeah,
but
maybe we should talk offline so I can better and get more into details. Yeah. I mean, at this point, if you can get the primary rays in your render to follow that thing, it works right off the bat on their holographic display and almost every other device we've tested. But maybe this is a deeper conversation we can take offline.
Yeah,
Any other questions as well, I'm happy to discuss if we're short on time. Great. Thank you very much, everyone.
Hi everyone, my name is Ehsan. I want to be talking about compiling HLSL shaders to SPIR-V using DirectX shader compiler. I'm going to start by giving a little bit of a background info for those who are not familiar with the project, following by some status of the project, feature coverages, how you can get started with using this compiler, and then I'll finish off by talking about some of the recent work that we've been doing in the compiler. DirectX Shader Compiler, or DXC for short, is Microsoft's next generation HLSL compiler It's the successor to FXC that's being deprecated. It is based on LLVM, and Microsoft open sourced this compiler in early 2017. And a few months later, we reached out to them and asked whether we could contribute a SPIR-V backend to their compiler in order to enable compilation of HLSL to SPIR-V. And the idea was to share a lot of code with Microsoft, to be able to have the front end parsed and the HLSL validated in the same code that Microsoft is doing, and building the abstract syntax tree, the AST tree, and then contributing the SPIR-V backend by us. There's obviously the Dixel backend, that's the Microsoft's IR, and they do their own set of transformations and optimizations on Dixel to target DirectX, and our backend will work off of the same tree to generate SPIR-V. And the SPIR-V that comes out of our backend is not necessarily valid SPIR-V, and it's certainly not optimal SPIR-V. So we imported Kronos Group's SPIR-V tools as an external GitHub submodule into the DXC project in order to be able to run multiple passes of validation, legalization, optimization on the SPIR-V that we generate, and run all these passes and make a very optimal SPIR-V before delivering it to the user. So the high-level goal is to make HLSL a first-class citizen for Vulkan. HLSL is a popular shading language, and there should be no reason why we shouldn't be able to use it to target the Vulkan Graphics API, and DXC is one way to make that possible. In terms of the current status, we heard from several companies during GDC this year that they have started using DXC for compiling their HLSL shaders to SPIR-V, so that's very encouraging and great to hear. We cover almost all native HLSL features now. We can compile all those features to SPIR-V. Many of these have been added recently, like enums, etc. It fully supports 16-bit types and 32-bit types. 8-bit types are currently not supported in HLSL itself. So if and when HLSL supports 8-bit types, then we have work to do to support it in the SPIR-V backend to target the Vulkan capabilities. It fully supports HLSL shader model 6.2 and below, and it can target Vulkan 1.0 and 1.1. And in terms of KHR and EXT extensions, we try to keep up and implement these extensions as much as we can, up to and including descriptor indexing. And in terms of vendor extensions, it is mainly up to the vendors to contribute to the compiler. Everything here is open source. For example, NVIDIA recently made a contribution for the compiler for the SPIR-V backend for compiling HLSL RTX to SPIR-V to target their ray tracing Vulkan extension. And we facilitated the doing code reviews, making sure enough testing is in place, documentation is in place, and landing the features in the master branch. And in order to make things easier for everyone and being able to integrate DXC into more workflows, we have worked hard to make it possible to compile DXC on Linux and Mac as well. Microsoft had added a number of Windows-specific things to the DXC repository, which made it impossible to compile DXC on those platforms. And we worked with them, and with their permission, we added a large amount of code to the repository to make it possible to compile and run DXC on these other platforms. And we've gone one step further and enabled build bots for these platforms, so that all pull requests and commits that go into the DXC repository pass building on these platforms. So if you want to give it a go and compile your HLSL shaders, the easiest way is to download pre-built binaries for Windows. These binaries are built using AppWare build bots on GitHub, and you can always get the top of the tree binaries and give it a try. If you want to know more about command line options that you want to use or how certain HLSL features mapped to Vulkan. We have a thorough user manual that I highly recommend reading. We tend to keep it very, very up to date. And if you want to go one step further and help us, there are instructions on how to build the XC from the ground up, and you can contribute to it yourself. So that was sort of a high-level overview of what the project is, where it stands. And next, I want to just briefly talk about some of the things that we've been doing on the SPIR-V backend side recently. We announced a lot of the stuff that we've been doing last SIGGRAPH. And since then, we have been doing a lot of rewriting, refactoring, and reorganizing the code to make it easier to maintain for the future and make it easier to develop for future Vulkan extensions. In order to do that, we have firstly added in-memory representations of SPIR-V concepts. So for example, we have faithful representations for SPIR-V instructions, basic blocks, functions, modules, SPIR-V types, all those things in the backend. For example, we have in-memory representations for SPIR-V instructions in a SPIR-V instruction class. But then we have also made a different class for every single SPIR-V instruction there is. And in many cases, we have multiple levels of inheritance where, for example, you can have different classes for all the SPIR-V instructions that can terminate a basic block, for example, or different SPIR-V instructions that can define constants. And the inheritance here allows us to leverage polymorphism to perform module traversals, SPIR-V module traversals in memory that I will talk about in a bit. So as I mentioned, the SPIR-V instructions, for example, all have an opcode, for example, that they can all use, or they can all have the source location where the SPIR-V instruction came from the HLSL, that can all live in the base class. But then each SPIR-V instruction can add its own members to the class. For example, for binary operations, you might want to have a left-hand side and a right-hand side, and you can use the base class pointer, the SPIR-V instruction pointer, to specify those. And all of these pointers allow us to really hook up all the instructions together in memory and be able to walk the SPIR-V module in memory and say, where did this operand come from and how did things happen? We can walk backwards and forwards. Similarly, we have the in-memory representation, or the IMR, for SPIR-V basic blocks, which among other things includes a vector of SPIR-V instructions. Or the IMR for SPIR-V function that, among other things, includes a vector of the basic blocks that are inside the function. And the in-memory representation for the SPIR-V module that, among other things, includes a vector of the SPIR-V functions that are inside the module. So all of these in-memory representations allow us to build the SPIR-V module in memory and then be able to traverse the module in multiple passes and make the final SPIR-V in multiple stages. It makes the code much cleaner, more organized, and easier to develop for the future. For example, you can have a traversal that goes through the SPIR-V module in memory and adds the necessary capabilities, or another pass that goes through and adds the necessary extensions, or another one that lowers AST types to SPIR-V types, or removes an instruction and replaces it with other instructions, things like that. So in order to make these traversals easy, we have written a base traversal class, SPIR-V visitor, and this makes writing traversals very easy. Writing a new traversal will be as easy as having a new class that inherits from the SPIR-V visitor and overriding these virtual methods. For example, if you want to write a traversal where you're going to go through your SPIR-V module, and based on the instructions that you're seeing, you want to add all the necessary capabilities. So the SPIR-V module says I'm going to iterate over my functions. The function says I'm going to iterate over my basic blocks. The basic block says I'm going to iterate over the instructions. And the SPIR-V instruction is where the callback happens to the actual capability visitor, for example, that is inheriting from SPIR-V visitor. And the code on the right-hand side is shared among all traversals, so you don't need to write it every time. It's there and it's already written. So writing a new traversal is really a matter of adding the code on the left-hand side and then invoking the traversal anywhere you want in the code. So for example here, for image operations, you can add the capabilities that you need for image instructions, or for if you want to add a shader or geometry or tessellation capabilities, you can do that based on your SPIR-V entry point instruction. So what these in-memory traversals allow us to do is not only make the code cleaner and better and easier to maintain in the future, but it also enables supporting features that we couldn't do before. For example, in HLSL, you have min types like min16 int, min16 float, etc. And these translate into having a relaxed precision decoration on the variables that have these types. But it also means that any arithmetic operation that uses these variables must have these decorations. So in an example here, if you have variable A and variable B that are relaxed precision, because the following addition operations are using A and B, they should all get the relaxed precision decoration as well. 1 is using A and B, 2 is using 1, 3 is using 2. So this is something that can easily be done with a IMR traversal. You can start with 2 decorations and then propagate them forward and end up with 5 decorations, for example. Or in HLSL, you have the precise keyword. If a variable is annotated with precise, it means that any arithmetic operation that can change its value should also be precise. For example, here you have variable v that's precise, so the arithmetic operations here should be precise, or the addition here should be precise. But also, the arithmetic here should also be precise because it can change the value of r, which will ultimately change the value of v. And again, precise translating to no contraction decoration in SPIR-V, and it has to be propagated throughout the module. So these traversals allow us to move backwards and forwards in the module in memory and do all the right things. So this is another thing that we've added recently, for example. And another thing that I mentioned earlier was we've added, say, a base class for all SPIR-V instructions, and they can all store the source location where the SPIR-V instruction came from. And talking to developers, everybody wants better debug information, of course. And being able to at least provide line numbers and file names is a big improvement. And we can do that by storing the source location of the HLSL source where the SPIR-V instruction was originated from. And in many cases, one HLSL line of code can result in several lines of SPIR-V code, which is fine. They can all point to the same source location. We have done this recently as well, so you can have multiple levels of HLSL files that include other files. And then in your SPIR-V, you will see things like variable B. You can see it's coming from, there's a preceding OP line instruction that says this variable is coming from new.HLSL line 1, column 17, or the function call to foo is coming from main.HLSL line 4. And this is some of the work that JBEC and our team has been working on, and it's recently landed in the master branch. One thing to notice about debug information is we generate all the OP line information in the SPIR-V, but once the optimizations run, there's a good chance that some of this information is going to be lost because the optimizations may inline things, move things around, and there are a couple of SPIR-V optimization passes that are written by the LunarG folks that makes it possible to maintain as much information as possible. So if you're looking at the line information, you should definitely consider using those in your optimization passes. And this was just sort of a brief highlight about some of the things that we've been working on, and there are many others, like giving developers more control over their descriptor sets and bindings, more command line options for selecting where you want your global C buffer to go or your default descriptor set to be. And I didn't put all these things on the slides, but This is basically some of the work that we've been doing. We're adding more and more features, and what I want you to take away from the whole thing is DXC is there for compiling HLSL to SPIR-V, and download it, use it, contribute to it, and let us know if you find any issues or you want to get any new features, feature requests. Please do them on GitHub, and we tend to respond to them really quickly. And I think that's my last slide. Thanks. Yeah, I think we have time for a few minutes for questions, if there are any. Sorry, go ahead.
Can you tell us if Google is putting any effort into supporting features in DXC besides the SPIR-V backend? For example, the removal of global variables is something that FXC supported, but DXC seems to not support that anymore. And this is, as far as I know, because Direct3D does this on the fly, this removal of unreferenced global variables, but Vulkan probably was not designed with that in mind, so this might be interesting for Vulkan.
Sorry, you're saying removal of unused global variables?
Of unreferenced global variables, that DXC doesn't remove that automatically anymore. And I've seen solutions where pre-processing is consuming HLSL, then rewriting HLSL, and then passing it to DXC to do that. Is Google putting any effort into contributing to the DXC project to support those features beside the SPIR-V backend?
Right. So there are there's a couple of components to it. One thing is, for this specific case, for example, I think the SPIR-V that we generate doesn't remove those by default, but then there are SPIR-V opt passes that can do that. So that removes the need for doing it in the HLSL level. And the other is, there are a lot of cases where if a feature is very useful, we get both Microsoft and ourselves to do it together so that both the Dixel backend and the SPIR-V backend can get it. An example of that is the register syntax for assigning descriptor set and bindings in HLSL. We heard that developers want to be able to specify just the space or the descriptor set without specifying the binding. So we implemented that in the SPIR-V backend, and we talked to Microsoft, and they found that feature to also be useful. So they implemented it for the Dixel backend, and now it's an official HLSL feature. So now you can use that new syntax in HLSL. So if there are features like that that you think is useful for both sides, if there's something that we can do in the front-end level, we work with Microsoft, and a lot of times they do it, and we just get the benefits in the back end. And sometimes if there's something that is very specific to the Vulkan side, we tend to do it in the SPIR-V backend or have SPIR-V opt optimizations that help with it.
Okay, thank you.
Yeah.
Anyone else?
And I'm going to be hanging around. If you have any questions, just come talk to me in the hallway. Don't be shy.
So thank you, Ehsan. We're now officially on break. We have 2 extra minutes of break. So we resume at 4:05 sharp, and Karen and Mark will be presenting about what LunarG is doing in the ecosystem. So we'll see you in a few minutes.
This will work with the presenter notes?
It was working fine for me. You often have to configure some.
Yeah.
Are you brave enough to go without power for 25 minutes?
Foolhardy, maybe?
All right.
Yeah.
No, you probably just have a better laptop than I do.
I don't know about that. Okay, so if I do...
Okay, you're in slides, and I don't know slides
so
terribly
I need
well.
to change this, right, to do extend. Okay. And go back here. And then present. And where's this guy?
This is, there you go. Now you're over there.
Okay, where do I? Oh, this is gonna kill Karen. Okay. Sweet. Thank you very much.
Okay, awesome.
All right. Can we do full screen? So it has this is the current slide, and you can see it right there, and then you just hit the right arrow, and then I can have my notes. So that's it. Just use the arrow keys. You could also use up and down, but just hit the right arrow key.
Okay. All is cool. Oh, and that's nice that they have that there.
Yes, it is.
Because then you can look more at the audience.
Mhm.
Well, I'm after Karen. hey, how's it going? Having a good show? Yeah. Oh, sorry about that. I was just wanted to make sure my setup was working. Hey, so you're using Google Slides? How did you get the main?
Plug in, and then you tell it you have to go to display settings and say you want to extend your desktop, and then you can just put the. Then you have to. Sorry.
Oh, I see. You slide it over.
Where is it?
Full screen.
It's full screen. How do you use it? 11? No, it's okay. All right. Okay.
There's something.
Okay, so yeah. So then I need to go over here, and this is weird. Which side's it on? There it is.
Present to view.
Yeah, let me pull this back over here. Make that full screen. And then go back over here. And, oh shoot. And then, is it 11 of 10? Do you remember? 12?
10. I'm going to go for 10.
No. 11.
11.
Okay.
Okay.
And then, yeah.
And then you can just.
And then you, yeah.
Awesome. All right. Thanks.
Sure.
Sorry about that.
No, no problem.
Welcome back. I think it's time. So for anybody who wandered in late, I'm sorry I don't have a copy of the agenda slide. We're in the second half of the Vulkan sessions. It is 4:06 according to my watch. So please welcome to the stage Karen Ghavam and Mark Lobodzinski. Okay, it's going to be Mark Lobodzinski from LunarG.
Hey everybody, my name is Mark Lobodzinski and I'm with LunarG. I help out some people there with the validation layers, and I need my glasses. And hopefully this won't take too long, and try not to make it too repetitive for the folks at SPIR-V yesterday. So some of these things would be much better covered by other people we work with, but I'm what you got. And hopefully it's at high enough level where that won't matter. So I'm going to do a couple, three of these things, and then Karen's going to wrap up. So the big change for the validation layers over the last quarter is that we used to have a bunch, and now we're down to one. And we got a lot of feedback from the community that having a changing set of layers was bad, and that also trying to figure out which order to put them in was a much larger problem than we thought it would be. So by having a single layer, which replaces the other 5, we're in control of that, and that also gives us some other advantages. So the big thing to us, the big advantage for doing this to us is maintainability, because we have one set of, there's a lot of crap that you have to do to just create the layer, and having one set of that instead of 5 or 6 or 7 or 8 makes things a lot better. But we also had some other advantages that came along with it. Another big change that's just gone in the last few weeks is that all of the code-generated files in the repo are checked into the repo. So if you're doing development for extensions or something, that's a little bit of a workflow change, but it makes everything a lot easier. We've, as part of that refactoring, all of the layer infrastructure and boilerplate has been moved out of the validation source files. So it's completely separate, and you don't have to deal with it when you're adding your own validation checks. That should make contributions simpler. And we're also in the middle of a big effort to pull out the state tracking from the validation. It was already fairly separate, but we're going to try to pull it out, and then we can reuse it across different validation objects. So the old layers are still in the SDK, but they are going away probably in a month or two. There's a lot of you are familiar with the standard validation layer. That's not really a layer. It's what we call the meta layer, which was kind of a hack to hide the layer order problem. That's already been changed, and it now only loads the Kronos validation layer. That too will eventually go away. So the big takeaway from my part of this talk is to use the Kronos validation layer. That will that evens out the story between mobile and desktop. It makes configuration easier, and then as we add different kinds of validation, it gives us a framework to hang those on without anybody having to change their apps or their operating systems or anything else. Let's see. So the way you control these things, you used to if you're doing work on an extension and you didn't want to load the unique objects layer, you just didn't include it in your list. But you can still turn those features on and off that used to correspond to the individual layers along with some other things. And to do that, I would recommend using vkconfig. This is a kind of a still in development front end to the layer configuration for features and options. And it will grow over time. It should get much better. But that will eventually probably be the easiest way to do it. You can also edit the layer settings.txt file. There's some secret environment variables which are documented in the repo. And there's the validation features extension, which was added last year. And you can use that in your application to turn those things on or off programmatically. And we'll be adding ons and offs to that extension over time. So the next thing is the GPU-assisted validation, and I'm just going to quickly run over that. Some validation checks are really hard to do on the CPU side. We don't know what happens until the shader's running. So GPU-assisted validation can help us out with those kind of things by doing the checks on the GPU. Right now, it's in the core validation object, but eventually it will be moved into its own validation object, and that's kind of nice because you won't need to have core validation saddled with all that source, and then also, if it's running by itself without the other validation, it should be a little more performant. And I think that right now, we just had some big addition from NVIDIA. It checks everything except for the mesh and task shaders. I'm not going to spend a lot of time here. There's some folks working on it back at home, but it basically, the layer intercepts your application calls, modifies the pipelines, and adds some validation checks to the shaders themselves. And then as the shaders run, they detect the errors, dump the output to a buffer in a descriptor set, which the layer then grabs on the way out and reports it to you if there's any problems. So there's three basic parts to GPU AV so far, and the first two are complete and were released in the most recent SDK. The other one is in development. The first thing we did, and the thing that got us to start working on GPU AV was buying the descriptor validation. That's been in for a couple of SDKs already. The descriptor indexing validation was just finished, and a lot of these checks were difficult, if not impossible, to do on the CPU. So we get extra coverage this way, and I think this is going to be much more valuable going forward. We had some good feedback in BOF yesterday about some other ideas for this. So the shaders are instrumented on the fly, and they validate that the indices are good. They detect out-of-bound indexing on the descriptor arrays, and if there's any unwritten descriptor elements, you'll get an error message telling you so. So Tony and Greg are working right now on the buffer device address GPU-assisted validation. That should be ready sometime in the third quarter, I think. In the GitHub for the Vulkan validation layers, there's a tracking issue. I think it's number 852. And if you've got any ideas for other kinds of this type of validation, you can just go add a comment there, and we'll put it on the list. So you control GPU AV just like you do the old layer features. You can use the VK config, the settings file, environment variables, or the validation features extension. And this will be the same for everything across the board going forward. Let's see. I'm going to talk just for a second about synchronization validation. We kept hearing from everybody that we should have better and more complete synchronization validation, and we meant to do that for a long time. John Zuloff has signed up for it, and he's working on it now. There's a couple of other infrastructure kind of things that have to happen first. But this will be a separate validation object just like GPU AV, and it will also be disabled by default. And we kind of foresee this future where you'll have your configuration application and you can turn it on and you'll just get regular everyday spec validation. And then you can decide you want to do your GPU-assisted validation, and you turn that on and run, and then you would turn on synchronization validation and run. If we had all of these things going at the same time over the long period of adding other validation checks, performance would just get worse and worse and worse. So some things are kind of meant to be run routinely, and some things are kind of meant to be saved for periodic invocations. Let's see, there's a tracking issue for this as well on the GitHub. It's going to be a big effort. It's probably going to start, you'll see checks start to show up in late fall or early spring, I think. And you control it exactly the same way that GPU-assisted validation is controlled with settings file, vkconfig, and the features extension. So with that, I'll turn it over to Karen.
Oh, thank you, Mark. I had him do the first part, which was a little more technical than what I wanted to do, but I'm just going to give a brief update on the Vulkan SDK and some other advancements we're doing there. So the first question I have is, you know, for several years we've been doing Chronos updates, and we've talked about the SDK, and I think we always just assume. Who in this room does not know what the Vulkan SDK is? Okay, so we do have a few. So I thought, it doesn't hurt to put in one slide in case there's someone who doesn't really realize what the Vulkan SDK is. So it was released with the 1.0 launch. Vulkan has been available since that time. And it's all comprised of the open source tools, validation layers, loader, et cetera, and other tools. LunarG was doing this SDK. We had some internal packaging tools. We actually, several months ago, put all these packaging tools, gave them to Chronos. So it's in a Chronos GitLab. So now this is going to enable some collaboration from Chronos on what's in the SDK and packaging and how we deliver it over time. So I just wanted to say, hey, in case you don't know what the Vulkan SDK is, here you go. And if you're curious what's in the Vulkan SDK, if you go to vulkan.lunarg.com, which is where you download it from, all the documentation for every utility or tool is out there at the download site. If you click on the docs button, you can peruse all the documentation. And also, a note is with each SDK release, which is based on a header version, we build the Vulkan specification and it's put out here. So you can look at the specification at 1.1.108 timeframe or 1.1.114 timeframe. It's always out here on the server for you to look at it. So as you're going through content in the SDK, you can use this guy as your documentation browser. Just want to make people aware of that. And wanted to give one more update. So there is an element that has been in the Vulkan SDK since day one. It's a VK trace, VK replay. It's a trace replay tool. It is still there. It will still be there for a while. But hindsight's always 20/20, and we learned a lot in that VK trace implementation, and we have re-architected or redone it with a much better solution called Graphics Reconstruct. It's in a GitHub in beta mode today. We already have some other people beginning to contribute and take it and use it. We are going to deprecate VK Trace, VK Replay sometime in the fall, which means that it will go read-only. It will still be out there if people want to use it, but we're moving our efforts over to Graphics Reconstruct for future trace replay, and that will eventually go into the SDK as well. Some preliminary benefits from it from a performance point of view. You know, we've seen about 2x frame per second improvements during capture replay, and file size is reduced greatly, at least by 50%, because we've integrated some file compression now during tracing. So VK Trace Replay really is kind of in a maintenance-only mode right now. We only fix critical issues there and avoid investing in that area because we're really focused on getting Graphics Reconstruct live. So some of the benefits is that unlike VK Trace, VK Replay, Android is given the same priority as desktop. And we've greatly improved the code generation. VK Trace Replay code generation was quite crude and clumsy. and hence new extensions, entry points quite often took a lot of manual work to get support for them. With this code generation improvement, Graphics Reconstruct can much easier keep up with the API spec as it evolves. The trimming is much more reliable. We're increasing portability between x86, x64, cross OS, Windows, Linux portability, so you could like trace on a Windows and replay on a Linux or vice versa if you needed. The ones in italics are ones that are still need to be implemented or may not be ready right at the time that we deprecate, but they will be there. For example, we will be working more focused on creating cross-vendor GPU portability, which is difficult to do with Vulkan with it being such a low-level explicit API. You can't necessarily just trace like on an AMD and replay in an NVIDIA. It doesn't work without some portability logic put in to do that. We have the LZ4 compression, which is really helping with the trace file sizes. And it's architected in a way that it will be very easy to add plugins, for example, to generate C code and other things as well. Extract shaders, replace them, things like that. And I was just going to end with another assumption I was thinking is that we get up here and talk every now and then, but I thought maybe not everybody really knows who is LunarG and why are we here and why do we talk at these Chronos events. So I just was going to bring that up one more time. We're a 3D graphics software consulting company based in Colorado. Valve and Google sponsor us to do all this Vulkan ecosystem work. And as such, we collaborate very closely with the Vulkan Working Group and watching the schedules and things they're doing to be as effective as possible in creating the Vulkan ecosystem tools. So just thought, for those of you who don't know who we are, that might be a good closing side. And don't forget about the networking session that starts at 5:30. We will be there. I have multiple LunarG engineers here. If you have any questions about anything in the SDK, in the loader validation layers, any of the tools that you're using, don't hesitate to come by. And of course, we have a free gift for you as well. So that's it. I think we have a few minutes if there are any questions. All right. Sounds good. That thing should be pushed over. With standing here, you can't see that display. It needs to go over 2 feet.
You know?
All right, sorry, just give me a second. Almost got this going. All right, full screen. All right, hello everyone. My name is Piers Daniell. I am the chairperson of the OpenGL and OpenGL ES working groups. I know this session is mostly about Vulkan, but I thought I'd sneak in and just remind everybody that OpenGL and OpenGL ES are still two very viable APIs, and there's still lots of investment going into it from the working group and from vendor companies. So we're still here. Don't forget about us. So quick OpenGL ES update. So the working group has been fixing bugs in the spec and the shader language spec, and we've been fixing bugs in the conformance. Vendors have been submitting conformance requests against OpenGL ES 3.2. There's been 20 plus new submissions in the last year or so, and those are the companies that have been making submissions. And in fact, if you look at the Android OpenGL ES 3.2 adoption statistics, you can see how the number of platforms out there that support OpenGL ES 3.2 has actually increased as a proportion to the other APIs. So OpenGL ES 3.2, with its, it adds geometry and tessellation, a whole load of other features, is now an even bigger target for developers. There's been a few new extensions, one ratified extension from Kronos, which I'll talk about later, and then a bunch of multi-vendor extensions. A lot of those actually are to do with expand on the Oculus multi-view extension. So if you're doing VR and AR kind of stuff and you just want to do multiple things with one draw, these extensions enhance that capability. There's also been a bunch of vendor extensions, a bunch from NVIDIA. A lot of those expose features in the new Turing GPU, and a few extensions from Qualcomm. A couple of those are related to foveated rendering, which is also would benefit VR. Quick OpenGL update. So there, again, like OpenGL ES, there's been updates to the spec, bug fixes. A lot of the bug fixes and suggestions for fixes we get actually come from the community via GitHub. We moved to GitHub a couple of years ago, and it's actually been a really great way to get issues, process issues, and also make changes and fix bugs. So you can either just file issues if you find things with the spec that are wrong, or you can actually contribute patches. There's been several new OpenGL 4.6 conformance submissions from AMD, Intel, and NVIDIA for new products and stuff like that. And we continue to fix CTS. New extensions, the KHR shader subgroup is the same as the OpenGL ES one. It's available for both APIs, and I'll talk about that in a bit. And there's a bunch of new multi-vendor extensions. And then for vendor extensions, NVIDIA has been the only one this year contributing, and most of those, again, are because of the new Turing GPU exposing features. So the newly ratified GL-KHR shader subgroups, this exposes the Vulkan 1.1 subgroup functionality to OpenGL and OpenGL ES. So basically what that is it provides instructions to do synchronized cross-thread operations. There's a bunch of things you can do: vote, arithmetic, ballot, shuffle. The little diagram here is an example of how you can use the shuffle operations to move in values from one thread to another. So all these operations basically work across all the threads within a warp or a subgroup, and can do various operations on them. And by using these, you can accelerate all kinds of different algorithms, reduction, convolution, and any other kind of parallelizable thing in a really efficient way. There's a beta driver of this available on the NVIDIA website if anybody wants to play with it. So there's some things that Vulkan has which OpenGL doesn't have yet. One of the things is ray tracing, for example. And for features like that OpenGL does not have, one of the options that you have, if you really need access to those features, is to use interop. These extensions have been out for a couple of years now, and they allow you to basically create objects in Vulkan or OpenGL and use either of those two APIs to create data or consume data in those memory objects, and then consume the memory objects in the other API. There is a little synchronization required, but it's all very explicit, and you can use one API's features in order to use the result of it in another API. And this is a really viable way of doing interop. And actually, there's an example of this that Dassault implemented recently. This is a proof of concept. This is their 3D experience Katia app. And basically, they used interop in order to add ray tracing to their traditionally OpenGL application. So Katia is an OpenGL application. It's been around for a long time, but they wanted to add some ray tracing features, in particular high-quality ambient occlusion and stuff like that, which, if you want to do it accelerated using the new ray tracing features, you basically have to use interop. And here's a proof of concept of it working. I'm going to show a quick video. So here they have an example of high-quality ambient occlusion running in Katia, and you can see how they switch between this video demonstrates how it switches between ambient occlusion on and off. Oh, except the video stopped. Oh no. Who's consuming bandwidth? Please stop. All right, let me restart it. Okay. Oh, sorry about this. It's not quite as seamless as I hoped. Anyway, this video is showing how that they've used ray tracing acceleration in Vulkan and incorporated the results of that into a traditionally OpenGL application. This particular thing is a real engineering data set for a car. It has 10,000 parts and 20 million polygons. And the results that they're getting here is basically a 10 to 20x improvement on performance over doing this on the CPU. So one single RTX 6000, which is what this is recorded on, is about 10 to 20 times faster than 24 CPUs in a cluster. And I have another quick video. So this is global illumination using Monte Carlo techniques. Again, this is stuff rendered in Vulkan and results brought over to OpenGL and incorporated with the OpenGL app. And I'm sorry, this video is not playing back either. Sorry. All right, so those are things that are missing in OpenGL, but you can use interop to get access to them. There is actually a whole bunch of stuff that Vulkan doesn't have that is in OpenGL. And that's a problem for people who have traditionally OpenGL applications and they want to move over to Vulkan, for example. And the Vulkan working group has been identifying these issues and trying to fill the gaps. So there's been a whole load of extensions added recently in order to fill these gaps. This is the full list. There's things in there that are in OpenGL 4.6, like the indirect draw. There's bindless in that list, conditional rendering, which has been in OpenGL forever. And finally, Vulkan has uint8 index type and transform feedback. But the two I'm going to talk about today is line rasterization and command lists. So one of the problems that Tom mentioned earlier in his talk is that Vulkan doesn't have an explicit way of drawing really high-quality lines. It kind of varies by implementation. So there's a new extension called ext line rasterization, which gives you far more control over the quality of the lines that you render. If you look on the image on the left, you'll see that especially that diagonal line near the bottom, you'll see how it alternates between single width and double width. That's one of the problems with the default line rendering of Vulkan. And to CAD people who look at lines all the time and are used to seeing high-quality OpenGL lines, that kind of quality is not really acceptable. So now there's an option in Vulkan to actually do Brissenden-style lines, and it's also line stipple. So you can get the more consistent quality on the right. So this extension was just released a couple of days ago. There's a beta driver available if you guys want to play with it. Another thing that GL has had for a little while is GL command list. It's an extension from NVIDIA. It's a really cool extension where you can use the GPU itself to create command buffers, and including lots of state changes. And the benefit of the GPU creating these command buffers is it can cull all the stuff that you can't see and all the useless stuff, create the command buffer, and then the GPU itself will consume that command buffer without any kind of CPU-GPU synchronization. It's an incredible extension, but Vulkan doesn't really have this yet. It has an experimental one that NVIDIA produced a couple of years ago, and we're now pushing to try and make this a multi-vendor and cross-platform. So on the right here, you can see one of the benefits of this extension. So recording 1 million draw calls with 131,000 state changes, which includes changing the shaders and VBOs and push constant stuff. If you recorded those commands on 6 threads on a CPU, it's 8.7 milliseconds. If you record that same stuff On a GPU, it's 0.36 milliseconds, so substantial savings there. And this extension is going to come to Vulkan real soon. So the point I'm trying to make is that both OpenGL, OpenGLES, and Vulkan, they're all very viable APIs. And we all love each other. And we love each other so much that Vulkan has actually become a platform for OpenGL and DirectX for emulation and porting. So like I mentioned in the previous slide, there's all these features being added to Vulkan to make OpenGL an easier target. And that's the case. And I think these things make it easier for other applications to either port or emulate on top of Vulkan. After I'm speaking, there's Erik who's going to talk about Zink, which is running OpenGL on top of Vulkan. And then there'll be a talk on Angle, which is running OpenGL ES on top of Vulkan. And that comes right after that. So that's what I wanted to say. I do have one quiz question. There is a prize. So the prize is this book. This is Ray Tracing Gems. If you remember the GPU Gem series, so this is now Ray Tracing Gems. So my question is, okay, whoever puts their hand up, or whoever I see put their hand up first and answers this question, will get this book. The question is, if you're an OpenGL application, how do you do ray tracing? Yeah. Yeah. Basically use interrupt with Vulkan. There you go. I'll give you this after. All right, that's all I had. Thanks very much, and I'll hand over to Erik. Thank you.
All right. Hi, my name is Erik. I work at Collabora, and I'm here to talk about Zink, which is an implementation of OpenGL on top of Vulkan. So first, I'm going to look at what Zink is, and to talk about what Zink is, I first need to talk about what Mesa and Gallium is. So Mesa is an open source implementation of several different graphics APIs. And Gallium is a hardware abstraction layer inside of Mesa. It has a state tracker and driver architecture, which means that the state trackers are implementations of the API states, and then that pushes down to the drivers. So the drivers are relatively simple. Mesa has a Gallium state tracker for OpenGL, and that's what we're targeting here. It also has state trackers for other APIs. Some of them are useful for us, like DRI, GLX, and WGL. OpenCL, and yeah, DirectX 9, and various video APIs. Mesa also contains a GLSL compiler, which is of proper high quality, and spits out an SSA intermediate representation called NER. So Zink is a Gallium driver in Mesa, and it outputs Vulkan commands rather than a command list for or a command buffer for a normal GPU. It includes a NER to SPIR-V compiler, and when we put all of these things together, we have a fully functional Vulkan to OpenGL translation layer. It's currently in early prototype stage, which I tend to say. We support OpenGL 2.1, currently only tested actively on top of Intel's ANV open source Vulkan driver. But some people have run it on other GPUs. There's some experimental patches around for some higher OpenGL versions and some more GPUs. It's not really kind of ready for prime time use yet. There's still much more work to be done, and it's currently out of tree in Mesa. That means that it lives in a fork. So yeah, why would we want to implement OpenGL on top of Vulkan? So we start with this. This is more or less a joke. There's a lot of implementations out there. They have differences, and that kind of can get tricky. But there's some more reasons than that. So I think there's three major reasons. And one is that Vulkan is the future of open graphics standards. But at the same time, OpenGL is a requirement for desktop. But we can also, in addition to this, enable more use cases, maybe. So yeah, Vulkan has been around for more than 3 years, which has been enough, I think, to say that it's a success. It's proven itself, and it's moving fast these days. OpenGL is pretty old by now, and it's moving at a much lower speed. It's not dead, but it's not exactly young and vigorous, I would say. So I think it's a pretty safe bet that Vulkan is going to be the leading high-end or high-performance API going forward. But yeah, so an OpenGL is an absolute requirement. It's very widely adopted, very widely used. We can't ignore it. Some applications will never be ported over to Vulkan. Some simply because of lack of resources. Some were already shipped a long time ago. Maybe the developers are out of business. Maybe the source code is no longer available. That kind of problems. Yeah, and some just don't really need the benefit of the increased or decreased CPU overhead. So, yeah. But yeah. We need to keep stuff working somehow, but especially in the open source world, it's much better for the community if we can implement an OpenGL driver once and everyone just have to develop one Vulkan driver for their new hardware. Yeah, and some of the more use cases here is so what kind of motivated me to start looking at this was working with GPU virtualization. If you're going to virtualize a desktop currently, you need to implement both virtualization for OpenGL and for Vulkan. And the virtualization code runs at a very high privilege level. Basically runs inside the hypervisor, or often does. It's much nicer or much easier to vet one set of Vulkan virtualization and do fully inside the guest the OpenGL to Vulkan. But besides that, maybe we can also bring the full OpenGL support to platforms that don't currently have full OpenGL. This can allow us to port some applications that currently won't run. And we can also maybe even build hybrid applications that uses both OpenGL and Vulkan, where Zink can maybe receive command buffers, for instance, directly into there. This can be useful for porting, gradually porting big applications. Yeah. So why I based this on Mesa is that's where the XKCD slide actually is a little bit serious. Implementing a complete desktop OpenGL implementation, that's a huge amount of work. Mesa already did the vast majority of it, so we want to benefit from that. Pre-existing solutions only solves part of the problem. Both Glove and Angle only do OpenGL ES. That's enough for getting rid of OpenGL drivers on mobile, but not on desktop. VKGL, which is a similar effort, only does OpenGL 3.2 core profile. So again, it doesn't replace for a lot of legacy programs. So the current state of it is that OpenGL 2.1, most functionality work. There's a few little features that haven't been dealt with correctly yet. For instance, the GL polygon mode can't do separate front and back states. Arbitrary texture border colors are unsupported. Flat shading uses the wrong provoking vertex. The wrong provoking vertex, so it misrenders flat shading. And edge flags, for instance, are completely missing. OpenGL 3, we have some patches for that. For that, we require transform feedback and conditional rendering, which we luckily have some EXT extensions for. Things that we still need to solve there is arbitrary primitive restart indices, but we can probably just rewrite the index buffer. Yeah, so OpenGL 3.1 to 3.3, there's some stuff to be done there. Geometry shaders and UBOs need work. OpenGL 4 to 4.6 has a bunch of challenges, but I can't really see anything that's a huge showstopper. It might need some boring emulation here and there, but so I'm gonna run a couple of demos here. Oh, this is this is Quake 3, I guess. So as you can see, this runs okay. I'm not aware of anything misrendering here. Yeah, it's a bit awkward with the oops. Something happened to my mouse cursor. Yeah, okay, I lost my mouse cursor. I was going to show you Blender. I have it here on my screen, but I can't move it over. So I'm going to just continue. Yeah, so there's some features that needs emulation. First thing is the provoking vertex. So the problem there is that OpenGL supports either first or last vertex as the provoking vertex. That is the vertex it will pick flat shaded colors from. Vulkan only supports the first one. We currently just ignore this and just use the wrong one. This, of course, causes rendering issues with applications that use flat shading. We have some options for emulation here. I have an implementation that does rewrites the index buffer, but it leads to some other problems. So my plan is to switch to a geometry shader that reorders the vertices out of there instead. That might also have some difficulties, but I think those are easier to solve. Yeah, the polygon mode, I don't really have a good fix for. So OpenGL can render front faces and back faces with different draw mode. They can expand to lines for a front face and fill for a back face. Vulkan doesn't have that. We can maybe fake it a little bit and render all the back faces first and all the front faces, something along those lines. It's not going to be great, it's not going to be correct, but maybe it works for some applications. Yeah, I'm not sure. Like, this is a pretty low priority thing for me. Texture border colors. So OpenGL allows you to specify any border color you want for textures, and Vulkan has a list of 3 different colors. I currently just hard-coded it to transparent black, which I don't really know of any application that uses it, so I haven't seen this be a problem otherwise in any other places than in synthetic tests. But we can solve it by injecting some shady code. It sounds awful, but it's actually not quite as bad. There's some pretty efficient ways of doing it where you can offload some of it to some of the pre-existing border colors and blend in the result in the end. Yeah, so in the future, there's also some kind of challenges. One thing is that I'm a bit worried about relying on EXT extensions for correctness. The problem is that they are probably not going to stick around forever unless they become a core part of Vulkan, and probably not even supported on all of the GPUs. So we're going to have some, I think, more robust solutions in the long term. For transform feedback, I think maybe we can get away with writing stuff to an SSBO. But there's similar issues with other extensions as well. So if you want to get involved in this, the code is in the freedesktop.org GitLab instance. There's some various branches there. There's an issue board and a wiki, but all of this will move to the main Mesa project once we're upstreaming, which I hope is soon. Yeah, and you can contact me via some of the magic of the internet here. And I would like to thank a couple of people who have helped out. Dave Early from Red Hat has done a lot of work, both on features and performance, and the Windows system integration code. Jason Ekstrand from Intel has helped me a lot with the shader compiler work, and a lot of other people from the Mesa project. And especially thanks to Collabora for sponsoring this work. And yeah, thanks to Kronos for letting me do this talk. So, that's it. Thank you. Yeah, so we have time for some questions if someone has anything. Yeah. Is there a mic? Is there a mic here?
Oh, my question was, do you have plans to submit your implementation to OpenGL conformance?
Not currently. There's some problems with that, especially in terms of how to do that. I would love to discuss this with Kronos, but I would assume like you would have to test for every hardware, every Vulkan driver you're on top of?
Well, we've done things like the RADV driver does not have to be tested on every AMD part. We encourage broad testing, but there are ways to do that. There are also some legal things which we worked out for RADV by having Free Desktop become, I think that's how it works. Is Free Desktop no, it's the parent. The ISF is something Software Foundation.
SPI or something?
It's SPI.
Yeah.
Is a Kronos member.
Yeah.
And so you can make submissions under that umbrella.
Yeah.
So there are ways to do it. We should just talk.
Yeah, I mean, Collabora is also a Kronos member, so...
Oh, right, sure. And that's how Intel does it, just...
Yeah. Yeah, so I could also imagine maybe like using Swift shader and submitting a general kind of on top of software rasterizer could make sense.
I'd just like to thank you very much for your work, because it's actually looks like it's saved our bacon a little bit for the software house that I work for. As people are probably aware, the OpenGL API is going away from macOS, and we're currently using Mesa and Zink on macOS to replace that for when it's finally going. We've done a fair amount of work on it and made a whole bunch of modifications, and we're wondering if you guys are interested in us contributing that back to your repository.
Oh, absolutely. Patches are very much welcome. So yeah, I would love to see patches.
Cool.
Hi, I think this project is really cool. What do you think is necessary to us also support like dry in addition to gallium well?
I didn't get that last part. Sorry. Yeah? Could you yeah.
I think you said that DRI support was experimental. What sort of things need to be fleshed out fully?
No, DRI support is not experimental, I think. But it is a requirement. So, for instance, NVIDIA doesn't do DRI drivers, so it won't work on NVIDIA right now, sadly. I mean, that can probably be fixed by some, other integration. It's just that hasn't been done.
Okay, thank you.
You're welcome.
Okay.
While you're walking, I'm going to do my one little prepared joke. Oh, that was corny.
Since we're in freelance, but it's not actually a question for Erik, it's a question for the gentleman doing work on macOS. So I just wanted to understand, are you going to take Zink and run it on top of Molten VK, on top of Madill, or? It's fascinating. Let's talk during the party.
Yeah, emulation on top of emulation is, I'm a little bit afraid of that. I think I would implement something like Zink, but outputting Madill instead. If I were to work actively on that. I don't have a Mac even, so I'm not going to touch that, but yeah. I mean, if it works, it works. All right, is that it? I guess so. Well, thank you, guys.
It's Jamie's him. I'm the next one.
What's this? The HDMI? Do you need this?
Yes. There's a dongle.
I have one.
Okay, thank you. There was one this morning. Go ahead.
Hello.
Oh, Alexis, is there a way to see my speaker notes? Is there a way to see my speaker notes? Is there a way to see my speaker notes?
All right, I'll just go without my speaker notes. Hi, I'm Jamie. I'm working at Google. I've been working on Angle for about 6 years. So I'm pretty sure that by now a lot of people have heard of what Angle is. In case you don't, Angle is a universal translation engine that only understands one language, in this case OpenGL, and it outputs to other languages, such as the ones I have listed here. Yeah, it started in around 2010, so it's almost 10 years old at this point, and it originally was conceived as a way to bring WebGL to Windows. At that point in OpenGL's history, there was very poor driver quality on Windows, and in some cases, your Windows computer might not even have OpenGL drivers at all. So by now, Angle's used as a WebGL implementation by Firefox and Chrome, so pretty much every Windows browser uses Angle. And more than that, this Angle's shader translator component is used in pretty much any device that has OpenGL on it. There's going to be some part of Angle running, at least validating your shaders. So at this point, our number of users is almost uncountably large. At a high level, like a lot of pieces of code, Angle is consisting of many layers. The application sits on top. The application calls it the entry points. The entry points call into our validation and state tracking layers. The state tracking layers call into the backend, and then the backend calls into the driver. One point that I want to mention is that Angle doesn't really have an intermediate representation. When the backend gets code, it looks pretty much like a GL call. So just to give you a quick high-level bird's-eye view of what the code looks like in Angle, this is in the state tracking layer. Here we're making a buffer data call. The first thing we do is we call into the backend with the same parameters you get from the input. We clear a bunch of caches, we update the state, and we notify the different components that depend on the buffer that things have changed, and then we just return control flow. If you look at this code, I'm hoping you're not very scared of what it looks like. We generally want to keep Angle pretty approachable, and when you see the code, you kind of can understand what it does without too much difficulty. So again, here we're in the back, now we're down a level, we're in the back end. In this case, we're in the Vulkan backend. And we create the object data store if necessary, and we update the data. I've taken away all the Vulkan commands for simplicity. Again, we want to keep the code complexity very low. We want to make it feel like if you want to contribute to Angle, that pretty much anybody could do so, and is welcome to do so. So our big project right now is focused on Android. You've heard about like Erik already talked about the OpenGL ecosystem right now. It's the same thing with GLES. Vendors right now on Android have to deploy both an OpenGL driver and a Vulkan driver. And OpenGL at this point is sort of in maintenance mode. But if you're a driver developer or device vendor, you need to update your Vulkan drivers to work on the new device, and as well as fix existing maintenance issues. At the same time, you're trying to deploy a new Vulkan driver and really focus on making that high quality. And without going into too much gory detail, that can be a bit of a challenge. So what we'd like to get to is allow the driver developers to focus on just shipping a Vulkan driver and have Angle implement a pretty decent job of GLES on top of that. Okay, so just a quick overview of our progress. GLES 2.0 is almost done. We have like 10 failures left to fix. Okay, so these numbers, by the way, were measured in terms of DEQP conformance rates, or the GL CTS, which we use a lot in our testing. And so in GLES 3.0, we're also getting pretty close to conformance, 90%. GLES 3.1, 80%, although there's a little bit of asterisk there, where a lot of those tests are returning unsupported, which is still technically okay. And GLES 3.2, we are actively scoping out. We're looking at the different features in GLES 3.2 and what kind of hardware and software requirements they require from the driver, and if we have to implement some sort of emulation, or if it's too difficult for us, if we need to work with the device developers to request extensions or add features that are optional. This bar on the bottom here is a progress of 3.0 conformance over about 3 months. So we're making pretty rapid progress. And our hope is that we can have 3.2 in EGL and GLES 1.1 conformant implementation around fall of next year. And just to clarify, this is not in any way suggesting this is like a release date or when we're going to start forcing things on Android. This is just when we hope to have Angle feature complete, and then from there we'll, take it up with our partners in the Android ecosystem to try and figure out what to do next. If you are interested in Angle's progress and how we're doing, you can visit the link there, which has daily updates of our pass rates on all our different OSs and target platforms. And yeah, it's been a pretty busy year for Angle. We're doing a lot of stuff, and we're trying to improve a lot. We're also trying to look at performance of Vulkan. It's pretty important to us, because obviously, if you're shipping OpenGL drivers on Android and you're running games on that, you don't want to regress performance. Currently, last I saw, our benchmarks were something like between 65 and 90-some% of native for the couple of benchmarks we were looking at, so there's quite a bit of work to do there. We're also looking at frame and capture replay solutions to beef out our testing, both for performance and correctness. And we're looking at bringing Angle to more Chrome platforms like Mac, Linux, and Fuchsia OS. And we also have sort of a skunkworks project on a desktop GL front end, which is just very early days right now. But yeah, we'd love to collaborate with you guys as well. Yeah, so that's all the slides I had for you guys today. Thanks very much for your attention, and yeah, thanks very much. So I presume there's a couple minutes for questions.
So I admire your courage in trying to tackle the problems of not only making this work correctly, but also make it performant. And I'm guessing that the 60 to 90% number is an average. How bad can it be?
The worst I saw was right now about 60-some%. But I only looked at a couple of benchmarks. We don't have very extensive testing. We're looking at GL Mark II, which is an open source benchmark. We're looking at GFX Bench, which has that classic T-Rex demo. And there's other GFX benchmarks. Then we'll continue to look at the other more bigger benchmarks. So the T-Rex it depended a lot on the off-screen versus rendering to the front buffer or the back buffer. And we were actually doing better when we were rendering to the back buffer, just because it's just a harder benchmark to get an advantage on. But the off-screen, we were like 65, and the back buffer one, we were like 90-some.
Hey, thanks for the talk. Can you tell a little bit about your approach about translating GLSL into HLSL for the DirectX backend?
Sure. The Vulkan one is somewhat similar, but we have basically, GL slang? Well, we both have a common ancestor, which is this 3.fx compiler that was released in like 2008 or something, or maybe even earlier than that. But it's an open source GLSL compiler that we both based our work on. So ours is highly evolved, and what we do is we come up with an EST parse tree, and then from the parse tree we output HLSL, and then the HLSL gets ingested by the Microsoft compiler. It's not the open source one though. We use the closed source version.
Thank you.
So are you planning on supporting strictly the baseline functionality of GLES 3.2 or desktop GL? Or are you planning on supporting like a selection of extensions, for example, things like interop that might help people work with the underlying Vulkan stuff too?
Like, you're wondering specifically what our plans are for the extensions?
If you have any plans, yeah, or if you entertain contributions for that kind of stuff, or if it's not your goals.
Oh, generally if people want to contribute it, we'll accept it. In terms of what we'll do ourselves, we haven't as far as I know, made an official statement or plan about it, but my guess is we'll just have to do as much as we can of what like a lot of existing drivers do. Maybe not like the most niche boutique stuff, but like if there's a wide availability of this extension, we also want to support it.
Kind of getting back to the question from the earlier session, is there a angle on metal option?
Yeah, it's a very similar answer. I saw a guy in the forums who actually made a Windows, he made an integration of Angle that worked on top of like a Molten VK, or I think Mozilla also has a similar project. So we have people who have already experimented with it, but it's running through Molten VK. We don't have any plans to make like a metal backend right now.
Any other questions?
Okay, thanks. Oh, yeah. Oh, I was going to introduce Alexis, who's working on Swift Shader.
Thank you. There we go. Okay, so I think I'm the last presenter today. By show of hands, who here has no idea what Swift Shader is? Okay, pretty good, pretty good. My hope today is that by the end of this talk, you know what it is. So what it is a graphics driver for the CPU. So we implement all of it on the CPU. So it's sort of what we're used to referring as a software renderer. But basically, we make it fast enough to use by using multicore, SIMD vectors, specialized instructions, so that it has a decent SIGGRAPH interactive frame rate. Why are we working on Vulkan with Swift Shader? Well, at Google, we're pretty much all in on Vulkan. Obviously, high performance is key, but every project is going to Vulkan. So it's mandatory for Android Q phones, except for extreme low end. Stadia will be using Vulkan on Linux. Chrome is adding Vulkan support. The Skia graphics library, which is one of the libraries used by Chromium, also has a Vulkan backend, and Project Dawn, also referred to as Web GPU, also has a Vulkan backend. So, Swift Shader Vulkan is there to make 3D universally accessible. So it has to, all of our projects have to run on every device, basically. So Android, so our goal, this is our goal, this is in the current state of things. So right now, Swift Shader has an OpenGL ES front end, as well as a Vulkan front end. And right now, it's not integrated in Chromium, as the Vulkan front end is just getting integrated right now. So right now, it's still using the OpenGL ES front end. So, so Android right now, we're hoping we'll be able to use OpenGL ES on top of Vulkan, and if the driver is unable to perform the required task, then it would go to Swift Shader. Similarly, on the web, Web GPU will be, so also Project Dawn, will have several backends like Vulkan and Metal and DirectX 12. But again, if the driver is blacklisted for some reasons, or if there's security concerns, or there's multiple reasons why sometimes we have to fall back to Swift Shader, that's what we'll do. At least it's better than getting a black frame. As I said, we currently have an OpenGL ES front end in Swift Shader, and we're transitioning to Vulkan only. A lot of the work that went into making Swift Shader Vulkan was related to getting SPIR-V on top of our library that's called Reactor. I'll talk a little bit about Reactor later. But basically, Reactor is a language that we use internally in Swift Shader that allows us to create just-in-time compiled code and that we can use in multi-thread afterwards. We have multiple backends. We use LLVM or Sub-Zero. Sub-Zero is a compiler that we have locally in Associator, but right now Vulkan only works on the LLVM backend. I will just talk about it very quickly. So Reactor, what it is so it's a language that we develop. It's high level, it's for code generation. So if any of you do code generation, it's very useful to do it very quick. So it produces code for a JIT compiler that will then compile it rather than execute it. So for example, in this little code sample that I put, you can see that there's an if with a capital I. That's actually a macro that we have that will generate a branch in for the compiler, right? And the plus equal, the A plus equal 10, the plus equal doesn't perform a mathematical operation. It adds the instruction to do a plus equal that will then be compiled by LLVM. So it allows us to write entire bits of code, including what we did with SPIR-V, very quickly and it's very readable. So, state of Associator Vulkan. So right now, we pass 100% of DQP VK conformance test suite. We only implemented Vulkan 1.1 mandatory features, so we don't have many extensions yet, but for all of the required things in Vulkan 1.1, we pass all the tests. It works on x86, on ARM, 32, 64-bit. We've tested all of those platforms. We have a Windows system integration for desktop and mobile. We already support Linux, Android, Mac OS. Win32 is done. We just need to land it. So where are we going with this? So our first future task is performance, because so far we've only cared about conformance. We wanted to make it conformant as fast as possible. We needed it, so right now there's multiple projects that need it, like Chromium, Android they have a bunch of test bots that are getting where they run different tests, and they need something to test it on, because our test bots don't always have GPUs in them, or for multiple reasons, and or for the Android emulator, if you're running it on a system that doesn't have Vulkan. Multiple reasons why all these projects need a software version of Vulkan. So what we're going to work on also is a tighter integration with Angle. So as I said, short term, we would like to get rid of our OpenGL front end and just rely on Angle on top of Associator for support for things like WebGL 1, WebGL 2, stuff like that. Right now, it's supported straight on top of Associator when the driver is blacklisted by Chromium. Yeah, and longer term, we might add OpenGL ES 3.1 and 3.2. For Chromium, so Chromium will itself have a Vulkan backend, so it needs to be able to test it, so that's where we come in. And again, for WebGL, as I already mentioned, and for Dawn WebGPU, will all also need to be tested on tribots, and again, we'll use Associator. Same thing for Android. What are the good points of using Associator Vulkan? So it can be used to anyone who wants to add an extension, for example, to Vulkan to quickly prototype it and see, is it working? Is it meshing well with other extensions? You can build your applications and Associator with Ehsan and TSAN, the address sanitizer or thread sanitizer, and fuzz it and see if you have any problems. Do you have any do you have any thread problems or out-of-bound memory accesses or anything, which you couldn't get with like a normal driver. With Associator, you can build it with Ehsan or TSAN and run your application on top of it, and you'll know if you're pulling the memory from under the driver at a bad moment. It allows to have platform-independent shader debugging. Associator runs pretty much the same way on every platform. It allows you to find, so we found a bunch of bugs in DQP, the Draw Elements Quality Program, the test suite. So we found a bunch of bugs where DQP was assuming the presence of some features and using it without testing if the feature was there. So, so we've contributed a bunch of fixes to DQP. We have macOS support, so we are compliant on macOS, which is something that Molten VK is working on, but we sort of have it now. Yeah, we can run all of DQP in under 15 minutes on a good workstation. So that's also pretty quick compared to waiting for a GPU to run the whole suite. So yeah, so in conclusion, it's conformance, consistent, hardware independent. We run on Windows, Linux, macOS, Android, Fuchsia, on x86, ARM, bunch of platforms. We run everywhere. It works pretty well. And as we go to Q&A, I'm just going to show you something if I can. I built it today, and it's from top of tree, so let's see if it works. So yeah, so this is Swift Shader. So what you're seeing is Vulkan run on a Mac OS, a compliant Vulkan running on a Mac OS. It runs at about 30 FPS, which is pretty good. This is not a super complex example, but it shows you that even with something that gets more complexity, you could probably get a couple of frames per second. You could test out your application, and you could see if you have any issues with it. So that's it for my talk. Thank you. Any questions? Everyone wants beer and pizza.
So this is great. Just a couple questions. One was the debugging. You said that it was good for debugging, which I think is great. Do you have any kind of special debugging environment around that, or is it just kind of like,
No, not specifically, but you can build Swift Shader in debug, and you can use any debugger that you would use normally. And then, like if you're on Windows and you're in Visual Studio, and you have a crash and somewhere, you'll have all the stack all the way down to the driver, which you wouldn't normally get. You can build Swift Shader in debug and see what's happening. It's very useful to find stuff like, as I was mentioning, like out-of-bound memory accesses and things that you would maybe not know, or things that a driver that goes very fast, maybe you would have trouble reproducing it, but then in Swift Shader, where everything is sort of always executed in a certain way, you would be like, oh, I have a memory out-of-bound access here, and if you do it again, you're probably going to be able to reproduce it. It won't be like one of those Eisen bugs that you can't, reproduce. That's very useful for that.
Yeah, no, that sounds great. I was also curious about, if you have any thoughts about performance scaling as volumes get very large, for example, or texture volumes get large. I work a lot on, scientific applications where we may have, multiple gigabytes of volume data. It seems like this wouldn't really suffer from the same swapping issues or, memory issues as a GPU version would, and maybe even perform better.
Right, so you could, depending on how much RAM you have in your machine, if you have like some big system with 128 gigs of RAM or something, you can probably do stuff that's just impossible normally. I don't really have an answer for that one specifically, but yeah, you could do some very large things, but it would probably still get, you will get bound by the vertex processing at some point. And it will get probably fairly slow if you have, 10 million, 100 million vertices or something running. Still running on the CPU here, so it'll take a little while, yeah.
Cool. Oh, I guess also, is there a repository or something we should?
Oh yeah, this is completely open source. I don't know if I mentioned it. Where is my presentation? Wait. Wait a second. Did I just kill it? I'll just reopen it. Just a second. Wait, I can check if. Yeah. Anyway, it's going to be on the slides when it's when they're made publicly available. Angle Swift Shader. There it is. Just going to go to the last one. So also, I'm going to mention that there's the repo. So swiftshader.googlesource.com is where you find all the source code. It's available. Also, if you have any questions past this day, you can write them to swiftshader@googlegroups.com. We're pretty responsive. Generally, we answer within a few hours of anyone posting questions. We have individuals who use it in place of their driver because they have very old machines or stuff, and we generally answer pretty quickly. Obviously, it's open source, so contributions are welcome also.